Hello fellow Sapiens, and welcome to Sleepless Homo, a quiet corner of soft science and deep time. Before we begin, take a breath. Let your mind slow down, whether you're getting ready to sleep, working late, cooking, driving, or just letting the world fade a little. This is your space to listen, learn, and wander calmly through history and science. If you appreciate thoughtful storytelling that stays humble to the evidence, not wild speculation, but curious science that admits what it doesn't yet know, please like and subscribe. It helps this kind of long-form education reach other sleepless minds trying to conquer the world with knowledge, not noise. And tell me in the comments, when do you listen? Before bed, on the road, in the shower, or while working with headphones? And if you happen to drift off during the story, timestamps in the description will guide you back. Because this one's worth hearing to the end. And as always, stay curious, stay calm. The story starts 4.5 billion years ago on a planet that was not yet kind. Earth, newly born, spun faster than it does today. Its surface was a restless ocean of molten rock, its sky a haze of carbon dioxide, nitrogen, methane and water vapour. Asteroids still fell like clockwork, and entire oceans boiled away under impacts large enough to tilt continents that didn't yet exist. But between these violent resets, something began to settle. The crust thickened, rain returned, and water, the softest of molecules, started carving a home for everything that would follow. Around 4.3 billion years ago, the planet exhaled enough to cool. Steam condensed into seas, minerals crystallized, and for the first time, chemistry had a stage large enough to perform for an audience that didn't yet exist. When scientists look at the earliest rocks from that period, what they see is not life, but hints that life could begin. Zircon crystals from ancient crust show oxygen isotopes suggesting liquid water. Around hydrothermal vents, iron, sulfur and nickel formed complex mineral layers that behaved a little like catalysts and a little like machines. These vents, chasms in the ocean floor where heat and chemistry collided, might have been where matter first started whispering to itself, not with words or purpose, but with gradients, pulses, and feedback. Inside those dark chimneys, iron and sulfur cycled electrons through microscopic pores, creating natural batteries. Each pore had slightly different conditions, some more acidic, some more alkaline. Molecules drifting between them experienced a kind of selective filter, a crude physical version of what biologists later call signal weighting. The vent walls didn't copy anything, but they favoured certain reactions over others, and in a world with no blue sky, favouring is everything. Modern experiments have shown that under these conditions, organic molecules like amino acids and simple sugars can appear spontaneously. Not from miracles, but from physics. The gradients of heat and charge in these vent systems act like primitive computation. They weight outcomes by energy efficiency. Over millions of years, these reactions didn't just repeat. They accumulated subtle bias. The planet began to remember, in a purely chemical sense, what worked. This is where the phrase signal weighting begins to make sense. Life may not have started with replication, as the textbooks once said, but with resonance. Patterns that persisted because their environment kept recreating them. Matter was not yet alive, but it was starting to listen to itself. The concept comes from systems theory and geochemistry alike. Every atom in a reaction carries information about what it can bind with, what it repels, and how stable it feels in a given environment. When many atoms interact under steady gradients, certain combinations appear more often. That's not randomness. It's selection before genes existed. The iron-sulfur minerals acted as primitive organizers. Their surfaces trapped carbon molecules, aligning them in repeating patterns that could both break apart and recombine, like the first hesitant words in a conversation between physics and biology. When scientists simulate these ancient conditions in the lab, they often see something strange. The longer the system runs, the less chaotic it becomes. Certain molecules begin to dominate, certain reaction pathways reinforce themselves. It's as if chemistry is finding its comfort zone, and that's the moment when the definition of alive starts to blur. If you looked into one of those vents with a microscope, you wouldn't see anything recognizable. No cells, no membranes, just shimmering fluids crossing boundaries of pH and temperature. But if you measured the flow of molecules, you'd find patterns that repeat, amplify, and stabilize. The vents were not just chemical factories, they were feedback loops, the kind of systems that later brains, ecosystems, and societies would echo in more complex form. Imagine early Earth as one enormous experimental lab, running 1 billion parallel tests for what stability looks like in a chaotic universe. Most reactions dissolved instantly, but some, like the ones along vent walls rich in iron and nickel sulfide, lasted a little longer. Every second of persistence gave them another chance to interact, combine, and evolve complexity. Life might not have started from a single lucky accident, but from trillions of micro-events quietly stacking probabilities. The world was not waiting for life, it was already rehearsing it. If we step back, this view challenges a century of biological storytelling. The traditional picture says life began when a molecule learned to copy itself, but copying by itself is brittle. A perfect copy dies the moment conditions change. Feedback, on the other hand, adapts. A system that weights signals, that rewards stability, punishes noise, and learns through cycles, can survive long before it reproduces. This is what the Zenodo paper on signal weighting suggests, that the boundary between chemistry and biology is not replication, but coupled feedback. Two processes that reinforce each other until persistence becomes inevitable. Consider how that looks in geological time. 4.2 billion years ago, the surface of the planet was mostly basaltic rock, constantly recycled by volcanism. Rainwater leached metals from those rocks, creating mineral soups. When that fluid met hydrothermal discharge, complex gradients formed, electric, chemical, and thermal. Each boundary acted like a decision point. Some molecules stuck, others drifted. Over countless cycles, the ones that stuck in just the right ways catalyzed more sticking. It's primitive, but it's logic. It's the same kind of logic your neurons use now. Voltage differences, thresholds, reinforcement, just written in sulfur and iron instead of sodium and potassium. And then, sometime around 4 billion years ago, those whispering reactions found rhythm. Chemical cycles began looping in synchrony with external events. Tides, day-night heat shifts, volcanic pulses. The planet's physical oscillations began syncing with its chemical ones. That's when life's tempo might have begun. Not replication yet, but rhythm. Patterns that repeated because the environment itself pulsed like a metronome. Some scientists call this the metabolic first model, life as energy organization before information storage. Others simply call it emergence, but the truth is, both are saying the same thing, that life began as feedback tuned to its surroundings. Of course, none of this is proven beyond doubt. The evidence we have from those earliest eons is almost erased by time. The oldest surviving rocks have been subducted, melted, and remade countless times. What remains are isotopic traces, subtle ratios of carbon, sulfur, and iron that hint something non-random was happening. A ratio that should be balanced in pure chemistry becomes slightly skewed, suggesting selective processes. We can't call that biology, but we can't call it chance either. It's the residue of matter that for a brief instant favoured one path over another. Perhaps the first whisper of intention, though not yet conscious, not yet aware. To call it signal weighting may sound modern, almost digital, but the term is simply a metaphor for how nature sorts noise from meaning. In a sense, every stable molecule is a memory of conditions that once allowed it. Every atom is a vote in a planetary conversation about what endures. Those first reactions were life's early dialect, chaotic, non-linear, self-correcting. There was no goal, just the physics of persistence, and in that persistence, chemistry started to resemble choice. There's a quiet irony in how similar this process is to how we, as humans, think. Our neurons strengthen the pathways we use most often. Our societies repeat behaviours that yield stability. Life, it seems, has always been a feedback machine. From minerals to mines, it learns by reinforcing what survives. The difference between a vent reaction and your memory is just complexity and time. The principle is identical. Keep the patterns that work, discard the ones that don't. That's not a metaphor. That's physics pretending to be intelligence. We don't know exactly how or when these reactions crossed the invisible line from chemical to biological. Maybe it happened multiple times and only one lineage endured. Maybe it never stopped happening, and we're still surrounded by micro-worlds trying again. What matters is that somewhere between chaos and order, stability became inheritance. The planet learned to remember what worked, and from that first flicker of persistence, everything else followed. Metabolism, replication, consciousness, civilization. The whisper became a voice. In the end, we may never pinpoint the birthplace of life, because life wasn't born in a single moment. It was assembled slowly, by countless small agreements between energy and matter. Each molecule that lasted a little longer was a vote for continuity. Each feedback loop was a rehearsal for awareness. If that sounds poetic, it's only because reality often is. Life didn't begin because the universe wanted company. It began because feedback cannot resist itself. When chemistry finds rhythm, existence follows. And that's where we leave this first trace of the story. In the deep, hot oceans of a young Earth, where rocks hummed softly to the rhythm of heat, and matter, for the first time, started listening to its own echoes. Can a planet have reflexes? That might sound like poetry, but 4 billion years ago, Earth began to behave like something alive. It started to regulate its own chemistry, to steady its fever swings, to buffer chaos with quiet corrections. Long before the first cell blinked awake, the world itself was already practicing balance. It didn't yet breathe or think, but it was beginning to learn the rhythm that life would later inherit. Feedback. After the violent centuries of bombardment and melting, the surface had finally cooled into a stable crust. Volcanoes still rumbled, but the rains that fell no longer vanished in steam. They stayed long enough to carve rivers, grind stone, and dissolve minerals into the newborn oceans. Carbon dioxide from the thick atmosphere met these waters and began its endless cycle, dissolving, reacting, and trapping itself in rocks. It's easy to forget that the earliest atmosphere was suffocating by our standards, heavy with greenhouse gases that would have roasted the surface. Yet somehow, the planet's chemistry kept the temperature in a narrow enough range for liquid water to persist. It's as if the Earth learned, purely through physics and feedback, how not to destroy its own experiment. This balancing act happened through a process that scientists now call the carbon silicate cycle. When carbon dioxide combined with rainwater, it formed a weak acid that slowly attacked silicate rocks on land, releasing calcium and magnesium ions into the ocean. There, those ions reacted with more carbon, forming carbonate minerals that sank to the seafloor. Volcanic eruptions later recycled those carbonates back into gas through subduction and melting, releasing them again into the air. The result was a planetary thermostat that adjusted itself over geological time. If the world grew too warm, weathering accelerated, pulling more carbon from the air. If it cooled, weathering slowed, allowing volcanoes to rebuild the greenhouse blanket. No intelligence guided it. No hand tuned the dials. Yet this loop mimicked what biologists would one day call homeostasis, the ability of a system to keep itself within bounds. Around 4 billion years ago, these geochemical reflexes began to shape every other process. The oceans that covered most of the planet acted as vast buffers, absorbing not only carbon but also heat. Even as the young sun shone roughly a third dimmer than it does today, the greenhouse atmosphere compensated enough to keep the oceans liquid. This paradox, a fainter sun warming a wet earth, puzzled scientists for decades until these feedback loops were understood. They revealed that Earth didn't need to be intelligent to be stable. It only needed chemistry with memory. Within these oceans, other cycles joined the chorus. Iron dissolved from seafloor vents reacted with sulfur to form minerals that locked away energy. Nitrogen fixed itself from the air into reactive compounds through lightning and volcanic heat. Every element, from carbon to phosphorus, fell into rhythmic exchange between rock, water, and atmosphere. Each cycle dampened extremes and reinforced continuity. This was not life yet, but it was a planet rehearsing the behavior that life would one day perfect. The art of staying alive by staying in motion. When we look at those cycles through the lens of modern Earth system science, what we see is signal processing on a global scale. The planet continuously filtered its own noise. Rising temperatures amplified certain reactions. Falling temperatures amplified their opposites. Positive and negative feedbacks interacted like notes in a self-tuning symphony. The entire crust, ocean and sky behaved as a distributed network that corrected itself without knowing why. Some geophysicists call this the first hint of planetary homeostasis. Others describe it as a kind of blind intelligence. Either way, it's hard not to hear the echo of what would later happen inside living cells. Consider the role of the oceans again. They weren't just passive pools, they were dynamic moderators. Their vast volume absorbed carbon dioxide and released it in pulses tied to pressure and temperature changes. Minerals precipitated and redissolved, keeping acidity near a steady level. Even small fluctuations in pH mattered, because chemical reactions depend on those balances. Too acidic and organic molecules would dissolve, too alkaline, and they'd stop reacting altogether. Somehow, the oceans hovered near neutrality, a chemical middle ground that allowed the first complex molecules to persist. It's tempting to imagine this balance as chance, but feedback is not luck. Feedback is inevitability in systems with many interlocking parts. Once one reaction influences another, and that second reaction loops back to affect the first, stability emerges not by plan but by structure. The Earth became the first self-correcting experiment in cosmic history. There's another kind of feedback worth noticing. Not chemical, but thermal. Volcanoes released heat and greenhouse gases, while radiation to space cooled the planet. Clouds formed and reflected sunlight, modulating temperature from above. The ratio between incoming and outgoing energy shifted constantly, but never catastrophically. Earth danced between ice and fire for hundreds of millions of years without falling permanently into either. That balance made the oceans long-lived enough for chemistry to grow complex. Other planets, like Venus and Mars, had similar starting materials but failed to sustain this equilibrium. Venus's carbon feedback spiraled into runaway heating. Mars lost its atmosphere to space, freezing its seas. Only Earth found the narrow corridor between chaos and silence, not by design but through countless feedback loops finding the least destructive path. The logic of signal weighting fits neatly here. Each environmental variable, temperature, pressure, gas concentration, acted as a signal. The reactions that stabilized those signals were rewarded by persistence. Over time, the unstable pathways died out. The planet effectively learned to prefer stability. It didn't think, but it responded. When volcanism increased carbon dioxide, weathering responded more intensely. When the sun brightened slightly, the oceans absorbed more carbon. Each swing triggered its opposite, like a pendulum that never quite stops but never collapses. That's how a planet without life began to act like something with reflexes. In modern science, we often describe these processes through equations, partial differentials balancing fluxes of mass and energy. But step back from the math, and what you have is something oddly biological. Homeostasis in cells later mimicked this exact principle. Sense deviation, counteract it, and maintain the conditions for complexity. The machinery of metabolism would later shrink this planetary behavior down to the microscopic scale. In that sense, life did not invent stability. It inherited it from the Earth itself. The ancient rock record tells us this feedback wasn't always gentle. There were episodes of global glaciation and warming that swung too far before correcting. Around 3.8 billion years ago, isotopic traces from ancient sediments show the first evidence that oceans had stabilized permanently. The chemistry of those sediments indicates a steady balance between oxidized and reduced compounds, a sign that the carbon-silicate thermostat had matured. The Earth had achieved something like a metabolic rhythm. If you imagine standing there, impossible though that is, you'd see a planet wrapped in thick clouds, a dim orange light filtering through, oceans steaming with energy, continents still small and raw. Rain hissed on hot rock. Rivers etched dark scars through the crust. Everything pulsed with chemical exchange. The world had no living eyes to witness it, yet it was already reacting, adjusting, surviving. If a planet could sigh, this is when Earth learned to exhale slowly instead of in explosions. This idea, that the planet behaves like an organism, later evolved into the Gaia hypothesis. Controversial at first, but increasingly useful in understanding long-term stability. We must be careful, though, not to romanticize it. The Earth isn't conscious, it doesn't intend, but its geochemical networks operate with such intricate feedback that they resemble decision-making. The planet's reflexes are simply the sum of physical laws interacting through time. Yet from those reflexes, life would later find the perfect conditions to emerge. buffered, tempered, and ready for persistence. Some scientists describe this stage as the era of planetary metabolism. The term fits because the entire crust and atmosphere cycled materials in a way not unlike breathing. Volcanoes exhaled carbon and water vapour. Rain inhaled them back into stone. Ocean circulation distributed heat the way blood distributes oxygen. And just as in modern organisms, none of these loops stood alone. They were nested within one another, each stabilising the next. That hierarchy of feedback would become the template for biological systems, layers of regulation built on top of older ones. By about 3.8 billion years ago, the Earth's climate had cooled enough for permanent crustal continents to form, and the carbon cycle had reached near equilibrium. The faint sun paradox was fully resolved by these internal feedbacks. The oceans no longer boiled or froze entirely. They stayed liquid for millions of unbroken years. This continuity was essential. Complexity doesn't need perfection. It just needs time. Feedback bought the planet that time. We often think of evolution as something that begins with biology, but the truth is that evolution, as a pattern of feedback and selection, began with the planet itself. The Earth experimented, failed, adjusted, and stabilised long before any gene or organism could take over the process. Those early cycles of carbon, sulfur, and water were the planet's first teachers of resilience. The blueprint for survival was already written, not in DNA, but in stone. Looking back, what strikes most scientists is how improbable it was that the right balance held. Any slight deviation could have ended it. Too much volcanic carbon, and the oceans would have boiled away. Too little, and they'd have frozen solid. But because feedback operates continuously, not consciously, the planet didn't need to be lucky every time, just persistent. Over geological ages, persistence wins. The world that learned to self-correct became the world that could host correction itself. Life. We don't yet know if this feedback principle exists on other worlds. Perhaps it does, quietly working beneath the frozen crusts of moons like Europa, or in the dense clouds of exoplanets we'll never visit. If it does, then feedback may be the universal signature of potential life, the pattern that marks a planet not as alive, but as capable of remembering its own conditions. When a system learns to protect its gradients, it's already halfway to awareness, and maybe that's what life truly is. Not a separate phenomenon, but a deep continuation of what the Earth was already doing. We inherited our reflexes from the planet that made us. Our bodies regulate temperature, pH, and salinity using the same chemistry the oceans mastered 4 billion years ago. The difference is scale, not principle. When you breathe, you echo the volcanoes and the rain. When you sweat, you mirror the weathering of rocks. The reflexes of the planet became the reflexes of the animal. So, can a planet have reflexes? The evidence suggests it can, not through mind, but through motion, through feedback loops that favour endurance over chaos. In those loops, the world learned its first lesson, that survival begins with balance. Everything that came after, from molecules to memory, would follow that same rule. The Earth was alive in the only way it needed to be, by keeping the conversation between energy and matter calm enough to continue. Before DNA, what remembered the pattern? Somewhere between 3.9 and 3.7 billion years ago, the world's chemistry began to cross an invisible line. The planet that had already learned balance now started learning persistence. Molecules that once appeared and vanished within seconds began to linger, to repeat, and most importantly to build upon their own results. This was the moment when matter started keeping score, not through memory as we know it, but through structure and repetition. The whispers of signal waiting that began in the vents of the young ocean turned into molecular echoes, shaping reactions that remembered what worked and forgot what didn't. To picture this, imagine the surface of a warm, mineral-rich pool somewhere along the ancient coastline. Tiny fluctuations in temperature, pressure, and concentration ripple through it like invisible tides. Carbon, hydrogen, oxygen, nitrogen, 4 simple elements, drift through this medium as countless reactive compounds. Most interactions end in silence, but every so often 2 molecules meet in just the right orientation and energy state to form a stable bond. This bond is not merely a product, it's a precedent. It changes the local environment ever so slightly, making similar reactions more likely. This is how chemical systems begin to show something like reinforcement, the first faint traces of what modern science calls autocatalysis. An autocatalytic reaction is one that helps create more of itself. It's the simplest known way for matter to remember without copying. When a product of a reaction also serves as its own catalyst, the process accelerates with each cycle. The result is a loop, a repeating pattern that grows stronger as it continues. It's chemistry's way of saying, "This works, let's keep doing it." In the laboratory, such reactions can be seen forming spontaneously under conditions that mimic early Earth: warm water, mineral surfaces, and a supply of small organic molecules. One famous example is the Formose reaction, where simple formaldehyde molecules polymerize into sugars. Left on its own, it runs chaotically. But introduce certain minerals, and the reaction begins to favor specific pathways, repeating them over and over. The system learns stability by weighting the chemistry towards successful combinations. Another candidate for early molecular memory involves short chains of amino acids known as peptides. When peptides form near metal sulfide minerals, they can act as miniature catalysts, binding to surfaces and helping other molecules assemble. These peptide networks don't replicate in the genetic sense, but they do propagate by facilitating their own patterns of attachment. Recent experiments have shown that such systems can even exhibit selection. Some peptides stabilize better than others, survive longer, and influence their surroundings to favor similar structures. The environment becomes a participant, nudging chemistry toward persistence. It's a quiet but profound shift. Evolution without biology. During this time, the Earth's oceans were thick with dissolved metals and gases. Iron, nickel, and sulfur were abundant, creating a rich palette of catalytic possibilities. Hydrothermal systems provided a constant supply of energy gradients, warm rising fluids meeting cooler seawater, generating conditions that allowed molecules to concentrate and react. These gradients were the stage upon which autocatalytic networks could perform. Each vent, each mineral surface, became a miniature laboratory running millions of parallel chemical experiments. Over time, certain reaction networks began to dominate. They didn't outcompete in a conscious way, but by lasting longer and producing more intermediates that fed back into the same loop. Scientists studying the origins of life sometimes refer to this period as the era of molecular ecosystems. Instead of single entities, the key players were networks of reactions. One reaction's waste became another's food. Heat and minerals structured these networks into repeating microenvironments, creating a hierarchy of feedbacks. The chemistry wasn't random anymore. It was organized by success, by whatever configuration managed to continue. This is the purest form of signal weighting at the molecular level, the selective reinforcement of reaction pathways that sustain themselves. We know from modern systems chemistry that even small sets of molecules can show emergent behavior when linked in cycles. For instance, a trio of interacting reactions may settle into oscillations, producing rhythmic changes in concentration, almost like a heartbeat. When energy input remains steady, these oscillations persist indefinitely. This behavior hints at the earliest version of a clock, not one that measures time, but one that encodes sequence. The order of reactions becomes a kind of memory, a map of cause and effect written in concentration gradients. It's primitive, but it's information. There's also growing evidence that these early reaction networks may have used surfaces as scaffolds for organization. Minerals like clays and metal sulfides possess crystal lattices that can attract and orient specific molecules. Once bound, these molecules react more efficiently, increasing the probability of repeating structures. Over many cycles, certain arrangements become favored. A pattern emerges on the rock itself. If the mineral surface breaks apart, some fragments carry the pattern elsewhere, seeding new reactions. The landscape becomes dotted with patches of chemical memory, each slightly different, each exploring new possibilities. In this way, the Earth's crust and oceans were not just passive containers, but active participants in the growth of complexity. They provided both the medium and the feedback. Some geochemists propose that early peptide-nucleotide interactions arose in exactly these environments. Short nucleotides could bind to metal surfaces, where peptides stabilized them against breakdown. The two molecules, though unrelated, helped each other persist. This mutual reinforcement, two systems coupling their feedback, mirrors the Xenado definition of life as the coupling of signal-weighting processes through mutualistic attraction. The chemistry of that ancient world was not yet alive, but it was already cooperative. It's humbling to realize that memory at its core might have begun not in neurons or genes, but in the alignment of molecules on stone. These were not memories of events, but of outcomes, a molecular record of what persisted. The same logic underlies evolution today: survival of the stable, persistence of the reinforced. Nature doesn't need foresight, it only needs feedback. Given enough time, feedback becomes structure, structure becomes function, function begins to resemble intention. Of course, this picture is stitched together from indirect evidence and careful experiment, not fossils. The rocks from that era preserve chemical signatures but no clear molecular relics. We infer these networks from what's possible, from what lab experiments reveal under similar conditions. We find that self-organizing chemical systems arise easily when energy flows through them. It's a comforting thought, that life's emergence wasn't an improbable miracle, but a natural tendency of complex matter under stable gradients. Still, we must admit our ignorance. We don't know which specific network crossed the line first, or if there were many false starts. The truth may be that the origin of life wasn't a single event, but an ongoing property of chemistry whenever it's given time and feedback. If we think about it philosophically, this stage marks the birth of inheritance without replication. In biological inheritance, information is passed by copying a sequence. In chemical inheritance, it's passed by maintaining a condition. When one reaction produces an environment that favours its own recurrence, the environment itself becomes the memory. This may sound abstract, but it's a principle that governs all self-organising systems, from chemical soups to planetary climates. Life, in every form, is an elaboration of this principle. By around 3.7 billion years ago, the stage was set. The planet now hosted a mosaic of reaction networks cycling through complex chemistry. The carbon cycle had stabilized, oceans had matured into steady environments, and molecular systems were experimenting with persistence. When we later find isotopic evidence of carbon fractionation in rocks from this period, lighter carbon atoms concentrated in ways that suggest selective processes, we may be seeing the fingerprints of these networks. Not full metabolism yet, but the prototype of it. So, before DNA, what remembered the pattern? The answer, as far as we can tell, is that the planet itself did. Its minerals, oceans, and energy flows acted as an external memory system, storing successful configurations and reintroducing them wherever conditions repeated. Life did not appear as an intruder into this feedback web. It was the next logical deepening of it. The first true cells would inherit not just chemistry, but the planet's instinct for stability and learning through repetition. It's easy to think of memory as something human, a whisper in the brain, a trace of experience. But memory is older than thought, older even than biology. It's a pattern the universe learned early. Keep what works, and let the rest dissolve. On that young Earth, memory was not stored in code, but in cycles, in the rhythmic persistence of reactions that refused to fade. In a way, the first form of learning was chemical. Every molecule that persisted was a tiny lesson. Stability can remember itself. Perhaps that's the quiet truth about our own existence. We are the descendants of reactions that refuse to vanish, the inheritors of molecules with memory. Everything you think, every neuron firing as you listen to this, traces back to the same principle that governed those ancient seas. Reinforcement through feedback. It's not poetry, it's continuity. At what point did chemistry start editing itself? Around 3.8 to 3.5 billion years ago, something extraordinary began to stir beneath the surface of Earth's oceans. After hundreds of millions of years of blind chemical improvisation, molecules began to do something new. They started refining their own instructions. The raw chaos of autocatalytic reactions, once driven purely by chance, began showing traces of logic, of selection, that operated not just on stability, but on accuracy. It was the dawn of coding, not in the digital sense we use today, but in the molecular sense. the emergence of rules that connected one shape to another, one reaction to its consequence. For the first time, chemistry was not merely reproducing patterns, it was interpreting them. This stage of Earth's history remains one of the most elusive and debated. We have no fossils of it, no microscopic imprints of these first molecular scribes. What we do have are experiments, analogues, and the universal genetic code itself, the single most ancient text still in circulation. Every organism alive today carries within it the traces of this early experiment, a code written in nucleotides and translated by proteins. But before that harmony existed, before the neat interplay of DNA, RNA, and protein, there was only chemistry, messy, error-prone, self-tuning chemistry. To imagine it, think back to the molecular networks we left in the previous part. Reaction loops scattered across mineral surfaces, capable of reinforcement but not yet of true inheritance. Those loops were powerful but fragile. They could grow, they could persist, but they could not record in any lasting way. Each generation of reactions had to begin again from scratch. Then, somewhere in those warm pools or vent systems, a new class of molecules entered the scene. Long chains built from repeating units that could both store information and catalyze reactions. These were ribonucleic acids, or RNA-like polymers, and they marked a shift from chemistry that simply happened to chemistry that remembered what had happened. RNA is unique among the known molecules of life. It can act both as a messenger and as a machine. It carries information in a linear sequence of bases, adenine, uracil, cytosine, and guanine. But it also folds into complex shapes that can accelerate reactions. It is, in a sense, matter reading itself. Modern research has shown that even small fragments of RNA can act as enzymes, known as ribozymes, capable of stitching together other RNA pieces or modifying their own sequence. That duality between structure and information was the breakthrough. It allowed reactions not just to repeat, but to improve. When scientists first began to understand this, they coined the term RNA world. But what the evidence now suggests is that RNA did not act alone for long. It likely shared the stage with short peptides, chains of amino acids that offered stability and catalytic diversity. The two molecules complemented each other. RNA provided template for consistency, while peptides brought flexibility and speed. Over time, their relationship deepened until it became interdependent. RNA sequences that could recruit the right peptides to protect them lasted longer, and peptides that stabilized the right RNA networks became more common. This wasn't just cooperation, it was coevolution. And at the molecular scale, coevolution means feedback. In those feedback loops, replication emerged not as a goal, but as a side effect. Systems that corrected their own mistakes naturally became more reliable at making copies. Each strand that folded in a way that resisted degradation slightly outlasted its peers. Each catalytic complex that favored error correction built resilience into the network. Over millions of years, these corrections became codified, chemistry teaching itself the value of proofreading. It's humbling to realize that the very idea of fidelity, the notion that information should be preserved, was not invented by life. It evolved from molecules struggling against entropy. At some point, a universal set of correspondences began to crystallize. Certain RNA sequences started linking with specific amino acids. These connections were not arbitrary. They emerged from the chemistry of affinity. Some amino acids bind naturally to codons or anticodons in RNA. Over time, these tendencies became formalized into the genetic code, a translation table that connected the world of nucleic acids to the world of proteins. This was one of the greatest revolutions in the history of the planet, the creation of a bridge between two kinds of molecules. From that bridge, complexity would surge like a rising tide. To call this a code might give it too much intentionality, but it truly functions as one. Each triplet of RNA bases corresponds to an amino acid, and the sequence determines the shape and function of the resulting protein. The astonishing part is that this code is nearly universal across all life today. That means it must have been established very early, before the diversification of any modern lineages, before the first cells as we know them. The consistency of the code across billions of years is one of the strongest pieces of evidence that all known life shares a common ancestry in this early molecular language. Error correction played a crucial role here. early molecular systems must have been plagued by mistakes. Copying long sequences from one generation to the next without proofreading would lead to rapid collapse. Yet we know from studies of modern polymerases and ribozymes that even primitive enzymes can evolve to reduce their error rates dramatically. Natural selection at the molecular level favoured those configurations that struck the delicate balance between fidelity and flexibility. Too rigid, and evolution would halt. Too error-prone, and structure would disintegrate. In that balance, life's first editors were born. The concept of signal weighting applies beautifully here. Every time a reaction produced a sequence that folded correctly or catalyzed efficiently, that configuration was reinforced. Unproductive sequences degraded and disappeared. The system didn't need foresight. It simply amplified what persisted and filtered what didn't. Replication was the outcome of this ongoing refinement. Chemistry discovering the algorithm of continuity. Recent research into ribozyme networks and peptide RNA hybrids supports this picture. In laboratory settings, scientists have observed small RNA molecules catalyzing the formation of peptide bonds, while peptides, in turn, stabilize RNA structures. This cross-catalysis forms the backbone of what might be called the first protogenetic networks. The molecules do not just coexist, they improve one another through feedback. It's chemistry in conversation, a self-correcting dialogue. At some point, this dialogue became a library. Once a molecule could serve as a template for another, and that relationship could persist over time, information itself became a physical entity. The difference between a mere reaction and a replicator is that the latter encodes memory in its structure. The genetic code, then, was not a sudden invention, but a slow crystallization of countless small associations, certain sequences that consistently led to favourable results. In this way, the code was written by chemistry long before life learned to read it. If we look closely at modern biology, the fingerprints of this era are still visible. Transfer RNA molecules, those small L-shaped adapters that ferry amino acids during protein synthesis, still carry chemical affinities to their corresponding codons, a molecular echo of those early associations. Ribosomes, the massive RNA protein complexes that translate genetic information today, are themselves ribozymes at heart. Their core catalytic activity still relies on RNA, not protein. Every living cell, in every domain of life, still performs this ancient ritual, RNA building proteins under the guidance of a code it helped create. It's an unbroken lineage stretching back almost 4 billion years. It's difficult not to feel awe at the simplicity of it. The universe's most complex structures, brains, ecosystems, civilizations, all rest on a logic first discovered by unthinking molecules in a dark ocean. The discovery wasn't conscious, but it was consequential. Chemistry learned how to encode its own corrections. It became capable of variation and preservation at the same time. In short, chemistry began to evolve. But we must be careful with our language. It's easy to slip into teleology, to speak as though these molecules were striving for purpose. They weren't. They were governed by physics and probability. What made the difference was not intention, but feedback. Each successful reaction became the foundation for the next, and small advantages accumulated over immense spans of time. The story of the genetic code is not one of design, but of discovery. The gradual emergence of order from the selective pressures of survival at the molecular level. When the code began to write back, it marked the end of chemistry as a one-way process. Until then, reactions shaped the environment but not the rules of their own creation. Now, sequences that succeeded in storing information could influence which reactions were possible next. This circular causality, information influencing chemistry, chemistry influencing information, is the defining feature of life. It's what distinguishes a living system from a merely reactive one. The molecules had, in a sense, begun to edit their own narrative. We may never know the precise sequence of steps that led from self-organizing chemistry to the first genetic code. The evidence has long since been recycled into new rocks and oceans. What we do know is that once information began to feed back into structure, evolution became inevitable. From that point onward, life was not just reacting to its surroundings, it was rewriting them. The code, once carved by the environment, had learned to carve back. In the silence of those ancient oceans, With no eyes to see and no voices to name it, the first great act of communication was underway. Chemistry had found a way to preserve its own successes, to correct its own errors, and to pass its lessons forward. The code was no longer a product of the world. It had become a participant in it, and from that quiet recursion, everything else would follow. Why did life need walls? Somewhere between 3.6 and 3.2 billion years ago, Earth's oceans were no longer just chemical playgrounds. The molecules we met before, the self-correcting, self-reinforcing networks of RNA and peptides, had begun to accumulate complexity, but they still suffered from a problem that every form of life since has had to solve: diffusion. Without boundaries, everything mixed, and when everything mixes, nothing lasts. Molecules drifted apart faster than they could react, energy leaked away into the vastness of the sea, and fragile patterns dissolved back into randomness. To endure, chemistry needed a way to stay together, to concentrate, to protect, to define a self. And so, before there were cells, there were boundaries that breathed. It is almost poetic that the structures that would one day define life began as the simplest of accidents: oily molecules trapped at the meeting place of water and rock. Fatty acids, the ancestors of lipids, formed spontaneously under conditions common on early Earth. Meteorites that have fallen to modern deserts still carry them, as do lab experiments simulating prebiotic chemistry. These molecules have a strange duality. One end loves water, the other hates it. When enough of them gather, they align themselves into double layers, the hydrophilic ends facing outward, the hydrophobic tails tucked inward, forming hollow spheres called vesicles. These fragile bubbles can grow, divide, and even capture other molecules without any biological machinery. They are chemistry's way of saying inside and outside. The emergence of this simple distinction transformed everything. Inside a vesicle, concentrations of molecules could rise high enough for complex reactions to occur. Outside, the environment remained a chaotic sea of possibility. The thin film that separated them wasn't a barrier of isolation, but a filter, a selective doorway that let some substances pass while keeping others at bay. In modern terms, this is signal weighting made physical. Every boundary amplifies certain signals and suppresses others. For early protocells, that meant letting energy in but keeping the useful results close. Laboratory work has shown that these primitive membranes were not the tight, protein-reinforced walls we see in modern cells. They were leaky, flexible, and alive with motion. Ions and small molecules slipped through them freely, maintaining an energetic conversation with their surroundings. Some researchers suggest this permeability was essential. Without it, the protocells would have suffocated, unable to exchange the materials they needed to sustain reactions. Their walls breathed, swelling and contracting with changes in acidity, temperature, and chemical gradients. It was a dynamic balance, stability through softness. Inside these vesicles, the co-evolving networks of RNA and peptides gained a new advantage. Concentration increased interaction. Interaction increased feedback. Reactions that once required the support of mineral surfaces could now happen in solution, within a confined pocket of order. A protocell that enclosed a more efficient network survived longer. One that trapped fewer reactants dissolved away. Through simple physics, natural selection began to act on the level of encapsulated systems. Life, in its earlier sense, became something that contained itself. At hydrothermal vents and volcanic shorelines, such vesicles would have formed continuously. Hot water mixing with cooler seawater provided the perfect gradients to assemble and rupture them, a natural cycle of birth and decay. Some may have coalesced into clusters, merging and exchanging contents before breaking apart again. These cycles of fusion and division created opportunities for molecules to recombine in novel ways, a primitive form of evolution by recombination, long before genes. Each new generation of vesicles experimented with chemical memory. The planet's oceans became a broth of living boundaries, each testing different solutions to the same ancient question: how to stay coherent in a world built for chaos. Researchers studying protocells today often speak of metabolism first, or membrane first, hypotheses. But these debates may miss the point. Boundaries and reactions were never separate inventions, they were partners. The membrane wasn't merely a container for life. It was life, just as much as the chemistry inside it. The flow of energy across that boundary defined what could exist within it. Every protocell depended on gradients, differences in charge, acidity or chemical concentration, to power its reactions. These gradients in turn were sustained by the semi-permeable nature of the membrane. Too open, and the gradient vanished. Too closed, and energy could not enter. Balance again. The same principle that stabilized Earth's atmosphere now played out at microscopic scale. Homeostasis written in lipids and ions. Experiments using mixtures of fatty acids and simple peptides show that membranes can even self-repair and grow. When more fatty acids are present in the surrounding water, vesicles naturally incorporate them, expanding until they split into two smaller spheres. If internal reactions generate amphiphilic byproducts, the vesicle effectively feeds itself, using its own chemistry to sustain its boundary. It is here, perhaps, that metabolism began to acquire a spatial identity. Reactions confined, reinforced, and recycled within a moving, responsive structure. The first living systems were less like factories, and more like weather patterns, transient, self-sustaining vortices of matter and energy. The boundaries also created something new in the logic of information. When RNA or peptide fragments were trapped inside a vesicle, they influenced only their own microenvironment. Their catalytic effects no longer spread across the entire ocean but remained local. This localization increased the diversity of experiments running simultaneously. Each vesicle was a tiny world with its own rules. Some produced more stable molecules, others burned out quickly, others merged and exchanged fragments. The sea became an archipelago of microscopic laboratories, all testing variations of the same fundamental design, a breathing boundary wrapped around chemistry that remembered. And yet these protocells were not isolated. Waves, currents, and temperature shifts constantly mixed them, breaking and reassembling their membranes. This created a delicate equilibrium between individuality and exchange. When two vesicles collided, they could merge, pooling their contents and allowing internal reactions to cross-pollinate. In this way, innovation spread without any genetic mechanism. The entire prebiotic ocean functioned as one vast network of interactions, its nodes defined by walls that existed only long enough to pass the baton of stability forward. What we glimpse through these reconstructions is not a sudden jump from non-life to life, but a gradual tightening of feedback loops. The first walls didn't isolate, they intensified. By limiting randomness, they allowed order to persist longer. Each generation of vesicles refined this balance, learning, if that word can be borrowed for chemistry, how to regulate its own permeability. Over time, these breathing boundaries began to incorporate helper molecules, like small peptides that stabilized their surfaces or channels that modulated flow. The stage was being set for the first true membranes of biological cells, but that evolution was still far in the future. For now, the protocells of the Archean oceans were fragile yet persistent, the first attempts of matter to define an inside. Geochemical evidence supports this picture. Ancient carbon deposits from around 3.5 billion years ago show isotopic ratios suggesting confined chemical processing, reactions that occurred in environments distinct from the open ocean. Microfossil-like structures found in some of the oldest sedimentary rocks, though controversial, resemble the residues of ancient cell-sized spheres. Even if these are not biological, they confirm that vesicle-sized compartments were abundant in the early Earth's chemistry. The difference between a bubble and a cell may be only a matter of complexity, not of kind. Philosophically, this moment carries deep meaning. The first boundary marked the first time the universe divided itself into self and environment. Inside and outside became separate categories of existence. From then on, life would always be defined by what it excluded as much as by what it contained. The membranes of protocells were not barriers to interaction, but frameworks for identity, the original act of self-definition. Without them, evolution could not have progressed beyond chemistry's noise. With them, individuality became possible. And yet these walls were never absolute. Even in modern organisms, membranes are porous, dynamic, and alive with exchange. The breathing of protocells echoes today in every living cell's transport systems, in the constant flow of ions, nutrients, and energy across its surface. We like to imagine life as separate from its environment, but it never truly is. The walls that make us are also what connect us. When we ask why life needed walls, we're really asking how complexity survives in a universe that tends toward disorder. The answer lies in balance, in boundaries that are strong enough to preserve structure, yet soft enough to let energy flow. The protocells of 3 billion years ago solved that puzzle not by design, but by physics. Their membranes breathed in rhythm with the planet's gradients, pulsing to the slow music of entropy and resistance. What we call the origin of life might better be understood as the origin of this delicate reciprocity, the dance between inside and outside order and exchange. A vesicle on the ocean floor could expand and divide endlessly, but without gradients, it would remain inert. With gradients, it thrived. That is the secret that every organism, from bacterium to human, still obeys. Life is the tension between containment and flow. We don't yet know which of those early protocells eventually stabilized into true ancestors of life as we know it. Perhaps many did, only to vanish. Perhaps the lineage that led to us was just one of countless bubbles that survived long enough to carry its chemistry forward. But one thing is clear. Once a boundary could breathe, the world would never be the same again. Inside was born. How did sunlight become a language? Around 3.2 billion years ago, the oceans of Earth were already alive with invisible experiments, protocells that breathed, fed on gradients, and learned to harvest chemistry for endurance. But something was still missing. Their world was dark. The planet's energy came mostly from the deep, from the slow generosity of geothermal vents and chemical reactions along the seabed. Yet above them, for over 1 billion years, a far greater power had been shining down, ignored. Light, abundant, relentless, indifferent, waited to be translated. Somewhere in those sunlit shallows, molecules began to do the impossible. They learned to speak with photons. We often imagine photosynthesis as an invention of plants, a green miracle tied to leaves and forests. But in truth, it is far older. One of life's first great negotiations with the environment. To use sunlight safely is not trivial. Photons carry energy in fierce doses, enough to rip apart molecules and destroy delicate chemistry. For early life, light was more threat than gift. Yet for some organisms, particularly those that lived near the surface where heat and radiation were constant, light offered both a challenge and an opportunity. It could drive reactions that no geothermal vent could match. All that was needed was a molecule capable of catching it without being destroyed. That molecule was pigment, small organic compounds able to absorb specific wavelengths of light and convert them into motion of electrons. Pigments are to early life what antennas are to modern communication, ways of tuning into a signal without being overwhelmed by it. The first pigments were likely simple derivatives of porphyrins and carotenoids, structures that could absorb energy and pass it along to nearby molecules. Over countless generations of chemical trial and error, some cells found ways to anchor these pigments into their membranes, connecting them to reactions that pumped electrons across the boundary between inside and outside. For the first time, sunlight was not just heat or light, it was information, guiding electrons along purposeful paths. This was the birth of phototrophy, the ability to use light to move electrons, to charge the molecular batteries that powered metabolism. Primitive versions of this process survive today in bacteria that use pigments called bacteriochlorophylls and retinol-based rhodopsins. These organisms don't release oxygen. They simply use light to supplement their chemical energy. They are the living fossils of a time when light and life were still getting acquainted, when photosynthesis was more negotiation than mastery. In laboratory experiments, scientists have reconstructed how such early systems might have worked. Simple pigments embedded in lipid membranes can, when exposed to light, generate voltage differences across the surface, tiny sparks of usable energy. These reactions are remarkably robust, suggesting that even before true photosynthesis, life may have already used sunlight to maintain its internal gradients. A photon striking a pigment could knock an electron free, which then travelled along a chain of molecules, each step capturing a fraction of its energy. This was electron transport in its infancy. light as the initiator of flow. Over time, these flows became structured. Life evolved proteins to hold pigments in place, aligning them with other molecules that could catch and pass electrons like a relay race. The process grew more efficient. Networks of pigments formed reaction centers, molecular circuits capable of splitting compounds and storing their energy in chemical bonds. The world that had once been powered only by the chemistry of the deep began to hum with energy from above. Sunlight had entered the feedback loops of life. This transformation reshaped the planet's ecology long before it reshaped its atmosphere. Photosynthetic bacteria colonized the upper layers of the ocean, forming mats and biofilms that trapped sediments and built structures known today as stromatolites. These living carpets grew in rhythmic layers, each generation building upon the next, capturing sunlight in a slow, architectural pulse that still echoes in the fossil record. To this day, stromatolites stand as monuments to the first organisms that learned to communicate with light. What makes photosynthesis so extraordinary is not just that it captures energy, but that it does so with precision. Photons arrive as discrete packets, each carrying just enough energy to move one electron at a time. Life evolved to use this granularity. Within the photosynthetic machinery, electrons are passed down stepwise through a chain of carriers, each slightly lower in energy, ensuring that nothing is wasted. It is, in effect, an ancient language of exchange, a protocol of energy transfer perfected long before human technology discovered electricity. This molecular conversation between light and pigment also created a feedback loop with the environment. Organisms that absorbed more light could grow faster, but too much exposure led to molecular damage. To survive, early photosynthesizers evolved strategies for balance. Pigments that protected as well as harvested. Molecules that could dissipate excess energy as heat or fluorescence. The dance between absorption and protection shaped not only metabolism, but also the diversity of pigment colors we see across the biological world. The reds, purples, and greens of modern bacteria and algae are echoes of this negotiation, each hue representing a different wavelength captured or avoided in the ancient solar spectrum. By 3 billion years ago, these systems had diversified. Some microbes used light to power the conversion of sulfur compounds. Others refined the ability to extract hydrogen from water, though not yet in the oxygen-producing form that would later transform the planet. The key was always electron management, ensuring that the captured energy could be stored as chemical potential rather than lost as heat. Pigments became embedded in intricate assemblies, the ancestors of modern photosystems where proteins and cofactors coordinated electron flow with exquisite precision. Even at this early stage, the relationship between life and light was mutual. As photosynthetic organisms absorbed sunlight, they changed the chemistry of their surroundings, altering acidity, releasing byproducts, and influencing mineral formation. These changes, in turn, affected the availability of nutrients, shaping which pigments were favoured by evolution. The planet's surface became a dynamic laboratory of feedback, with light guiding life and life reshaping the light environment. Over millions of years, these interactions began to stabilize the surface energy balance, cooling parts of the planet and influencing the color of its seas. Modern research into the evolution of photosynthesis suggests that this process occurred in stages. The earliest forms likely relied on a single photosystem, a simple chain of reactions that cycled electrons through the same pathway repeatedly. Later, some lineages developed a second photosystem, allowing them to extract electrons from new sources and store energy more efficiently. This innovation would eventually lead to oxygenic photosynthesis. But during this window in history, light was still being tested as a tool, not yet a revolution. What mattered was that life had learned to negotiate with it, to use sunlight as both signal and sustenance. There's a quiet poetry in realizing that our entire biosphere runs on this ancient language. Every green leaf, every drop of chlorophyll in the ocean, every photon that feeds a forest, all are descendants of those first conversations between pigment and light. When you see sunlight glinting on water, you're watching a dialogue that began billions of years ago, a conversation that turned a hostile star into a partner in life's story. And like any language, it evolved syntax and grammar. Reaction centers became more complex. Regulatory networks developed to control light harvesting according to the time of day, and molecular antennae expanded to capture more of the spectrum. Eventually, life learned to time its processes to the sun's cycles. The first biological clocks, primitive but effective, synchronizing metabolism with dawn and dusk. Light became not just energy but information, telling organisms when to feed, when to rest, when to divide. Though we can recreate some of these early processes in the lab, many details remain unknown. We still debate how and where the first phototrophic organisms arose, whether in shallow coastal pools, hot spring terraces, or deep sea settings where infrared light from hydrothermal activity could be harnessed. What's clear is that once light entered the equation, life's tempo changed. Energy became abundant and evolution gained speed. Complexity flourished wherever photons met pigments that could interpret them. There's something humbling in that. Life's first use of light wasn't about seeing or even knowing. It was about learning to listen to the sun without being destroyed by it. The pigments that now colour every ecosystem were once shields against radiation. Survival came first, then comprehension. The ability to transform light into energy may be the most elegant adaptation nature ever discovered. Not because it is perfect, but because it turned danger into dialogue. In a way, the story of photosynthesis is the story of negotiation itself. Light does not compromise. It arrives as it always has, relentless and pure. Life learned to take only what it could handle, to filter, to reflect, to balance. In that restraint lies the secret of endurance. The first negotiators of light didn't conquer their environment. They learned to translate it, and in doing so, began a conversation that continues in every blade of grass and every breath of air we take. What happens when a microbe changes a planet by mistake? Around 2.5 billion years ago, the Earth underwent one of the most profound transformations in its history, and it was not planned, not directed, not even understood by the life that caused it. A single type of microorganism, small beyond measure and unaware of its own consequences, altered the chemistry of the entire world. It filled the air with a new gas, one that would kill most of its contemporaries and rewrite the rules for everything that followed. That gas was oxygen, and the story of how it arrived is one of the greatest accidents in the history of the cosmos. The world before this moment was alien by every standard we know. The atmosphere was dense with carbon dioxide, methane and nitrogen. The oceans were dark, rich in dissolved iron, and largely anoxic. Life, mostly microbial, thrived in these conditions, feeding on chemical gradients rather than air. The sunlit layers of the ocean shimmered with photosynthetic bacteria that had learned to use light, but not yet in the way modern plants do. They relied on sulfur or iron to carry electrons, leaving the environment chemically reduced. Then, sometime before 2.5 billion years ago, one lineage of bacteria stumbled upon a new trick: splitting water. Water is abundant, but it is chemically stubborn. Breaking it apart requires enormous energy. When a certain group of microbes, the ancestors of what we now call cyanobacteria, evolved a molecular system capable of doing this, they unlocked an endless supply of electrons for photosynthesis. The side effect was oxygen. To the bacteria it was merely waste, an exhaust molecule diffusing away into the ocean. But to the rest of the planet it was a toxin. At first, the oxygen didn't go far. It reacted instantly with iron dissolved in seawater, forming rusty sediments that fell to the ocean floor. These layers of iron oxide, now known as banded iron formations, still stretch across continents, recording this slow chemical awakening. Each band marks a pulse of oxygen production and destruction, a chemical tug-of-war between life and geology. But oxygen is a persistent gas. As photosynthesis continued, the ocean's store of reducible minerals became saturated, and oxygen began to accumulate first in water, then in air. The shift was gradual but unstoppable. Over millions of years, the atmosphere changed from reducing to oxidizing, transforming every chemical pathway on the planet. Molecules that had been stable in the old world began to fall apart in the presence of oxygen. Methane, a powerful greenhouse gas, was broken down, cooling the planet dramatically. Iron that once coloured the oceans dark dissolved less easily, leaving the water clearer and the skies eventually blue. It was as if the planet had inhaled for the first time and almost choked. This event, known as the Great Oxidation, was not a single moment but a drawn-out revolution lasting hundreds of millions of years. Its consequences were both catastrophic and creative. Most anaerobic organisms, which had thrived in the absence of oxygen, found it lethal. Oxygen atoms are highly reactive. They rip electrons from other molecules, damaging cell membranes and genetic material. For early life, this was poison. Vast portions of microbial ecosystems perished or retreated to the few oxygen-free refuges that remained. Deep sediments, hot springs, or the guts of other organisms that would later evolve. Yet, for a few lineages, the poison became an opportunity. Oxygen's reactivity also made it the most efficient electron acceptor known. Organisms that could harness it could extract far more energy from their food. What began as a global crisis slowly became a new frontier of metabolism. Microbes evolved enzymes and pathways to manage oxygen's dangers. Antioxidants, catalyses, and superoxide dismutases, molecular shields that detoxified the reactive forms of the gas. Some even began to exploit oxygen deliberately, using it to burn organic molecules in controlled ways. The chemistry of respiration was born. This shift marked the beginning of a new planetary feedback loop. The more oxygen accumulated, the more energy life could access, and the faster it could grow and reproduce. But growth also consumed nutrients, altering the cycles of carbon, nitrogen, and sulfur. The Earth's entire system reorganized around this new gas. Sedimentary rocks from this period show sudden shifts in isotopic ratios, clear signs of atmospheric oxygenation. Sulfur isotopes, once fractionated by ultraviolet light in an oxygen-poor atmosphere, suddenly lose that pattern, evidence that a protective ozone layer had begun to form high above. The air had changed, and so had the light itself. Still, it is important to remember that this transformation was not inevitable. It required a fragile balance between biology and geology. Oxygen might have vanished again if volcanic gases had continued to consume it, or if organic matter had been fully recycled instead of buried. What tipped the balance was burial. Carbon that was photosynthetically fixed but not reoxidized, locked away in sediments. Every atom of carbon buried as rock left behind an atom of oxygen in the air. In this sense, the Great Oxidation was not just a biological event, but a geological one, a planetary bookkeeping error that got out of hand. As the atmosphere changed, so did the climate. The reduction of methane cooled the planet, possibly triggering global glaciations, ice reaching the equator, oceans frozen over for tens of millions of years. These snowball Earth episodes may have been the first times the planet's climate feedbacks were pushed to their limits. Life clung to survival in pockets beneath the ice, around geothermal vents, and within thin meltwater channels where light could still reach. Those that endured emerged into a transformed world, clearer skies, rust-coloured soils, and a new palette of chemical possibilities. Among the survivors were microbes that had adapted to tolerate oxygen internally. Some had evolved metabolic cycles that used oxygen in small, controlled doses to extract energy with unprecedented efficiency. The molecules that supported this process, the precursors of cytochromes, quinones, and heme groups, became the foundation for the respiratory systems that still power our cells today. These early oxygen-tolerant microbes were not yet complex in structure, but they were profoundly advanced in chemistry. They had turned a deadly byproduct into fuel. From this moment onward, the direction of evolution tilted toward those who could manage oxygen's double nature, both destroyer and giver of life. It became the central paradox of biology. The gas that enables high-energy metabolism also accelerates decay. Even now, in every breath you take, that contradiction remains. Oxygen grants power but demands maintenance. It gives us endurance, but it also ensures we will eventually age. Life has never truly resolved that trade-off. It has only learned to negotiate with it. What makes this transformation so striking is that it reveals the planet's sensitivity to feedback. A single metabolic innovation, the splitting of water, cascaded into geological and atmospheric change. Once again, Earth behaved like a system that remembers. The accumulation of oxygen altered volcanic chemistry, ocean circulation, and even the colour of the sky. The feedback between biology and the environment became a defining feature of the planet. Life was no longer simply reacting to conditions, it was setting them. We still debate the exact timing and tempo of the Great Oxidation. Geological records show smaller whiffs of oxygen earlier, followed by a steep rise around 2.4 billion years ago. Some scientists think these early pulses were temporary, erased by volcanic gas release, while others suggest they represent localized oxygen oases, microbial communities pioneering the air long before it became global. Whatever the case, the transition was not smooth. It was a saga of false starts, feedback crashes and recoveries. The Earth, once again, learned through iteration. What began as a metabolic shortcut for one lineage became the first planetary scale crisis, and, ultimately, the first planetary scale stabilization. In the long run, oxygen paved the way for more complex energy systems, larger organisms, and faster evolution. But at the time, it must have been a silent catastrophe, invisible, yet total. Imagine being a microbe in that ocean. Your chemistry, perfected over millions of years, suddenly turns lethal. The very water around you becomes corrosive. The sky brightens. The rocks at the bottom change colour. You wouldn't know it, but the planet you live on has begun a new chapter, one you won't survive to read. When we look back at this event, it's tempting to call it progress, to see oxygen as destiny. But there's no intention here, no grand plan toward complexity. The microbes that oxygenated the Earth didn't know they were changing anything. They were only following their own chemical logic, their own narrow survival. The transformation of a planet was the side effect of life's metabolism, a cosmic accident that proved irreversible, and that may be the most astonishing part. For all our technology, for all our analysis, the most important atmospheric engineering in Earth's history was done unwittingly by bacteria. They never sought to create a habitable world, and yet here we are, breathing the air they made. In that sense, we are the unintended legacy of an ancient mistake. Oxygen is our inheritance, and like all inheritances, it carries both gifts and debts. We often talk about the Great Oxidation as the moment the world woke up. But perhaps it's more accurate to say it began to dream differently. The chemistry of the planet reorganized around a new kind of energy, one that demanded caution and rewarded adaptation. Those who learned to live with oxygen gained power. Those who couldn't vanished. The planet learned to metabolize itself. Why did one microbe decide not to digest the other? Around 2 billion years ago, the Earth was a world of single cells, each fiercely independent, each powered by the quiet chemistry that had survived the Great Oxidation. The air was still thin, the seas still mineral-rich, and the continents only beginning to assemble into the recognizable shapes we know today. Life had weathered catastrophe and learned to live with oxygen, but evolution was running up against an invisible wall, the limits of energy. Metabolism was efficient, but not efficient enough. Every reaction cost power, and the scaling complexity meant needing more of it. Then, by accident or persistence, two cells crossed paths in a way that would alter the history of biology. One engulfed the other, and instead of digestion, a negotiation began. No one can say how many times such encounters happened before it worked. Perhaps it was rare, perhaps inevitable. We only know that somewhere in those ancient oceans, an archaeal cell, a simple but sturdy microbe, managed to take in a bacterium that could handle oxygen exceptionally well. In most cases, the invader would have been broken down for nutrients, but this time it resisted digestion. It stayed alive inside its host, burning oxygen and producing energy-rich molecules in return. What began as an act of predation became a partnership. Over generations, this living arrangement stabilized into a single, shared life form. The internal bacterium became what we now call a mitochondrion, and its host evolved into the ancestor of all eukaryotic cells, every plant, animal, and human included. 2 genomes, 1 house. This event, called endosymbiosis, is among the most remarkable transformations in evolution. It represents not just cooperation, but integration at the deepest level. 2 separate organisms fusing their metabolisms, their genetics, and their fates. The host provided protection and raw materials. The symbiont provided energy in the form of adenosine triphosphate, or ATP, the universal currency of biological power. For the first time, a cell could generate orders of magnitude more energy than before. That energy surplus would later make possible the rise of complexity, larger cells, internal compartments, and the biochemical luxury of innovation. But in its early days, this union was precarious, full of conflict and compromise. Modern molecular studies still reveal the scars of this merger. Mitochondria retain their own tiny genome, a relic of their bacterial ancestry, separate from the DNA housed in the cell nucleus. They even reproduce independently, dividing within the cell like miniature organisms. Yet they are no longer free. Most of the genes once carried by the ancestral bacterium have been transferred to the host's nucleus over evolutionary time. This migration was not a tidy process. It was genetic chaos. Fragments of bacterial DNA slipping into the host genome, some lost, some repurposed. The result was a new kind of organism, a chimera whose identity was shared between two lineages. At its core, endosymbiosis was about communication. The two genomes had to coordinate thousands of reactions to keep metabolism running smoothly. When one produced proteins, the other had to supply matching counterparts. When one regulated energy output, the other had to adjust demand. This was signal weighting on a cellular scale. Two feedback systems learning to cooperate. In a sense, the eukaryotic cell became the first networked society, a microscopic democracy of organelles negotiating in real time. It was not harmony so much as stable tension. Energy, as always, drove the terms of this partnership. The mitochondrion's chemistry exploited oxygen's hunger for electrons, channeling that reactivity into a carefully controlled process called oxidative phosphorylation. It was a masterpiece of molecular engineering, turning chaos into current. Electrons flowed through membranes, protons were pumped, and ATP molecules were assembled like coins in a mint. Each mitochondrion was a power plant, and its host cell the city it fueled. With this new internal energy source, cells could afford complexity, bigger genomes, slower replication, and elaborate internal organization. Evolution had discovered the biological equivalent of the Industrial Revolution. But every revolution comes with politics. The presence of two genomes in one cell created potential for conflict. Mitochondria multiplied on their own schedule, sometimes more than the cell needed. Their interests did not always align with their hosts. Over time, natural selection refined the relationship through control mechanisms. Host cells evolved ways to regulate mitochondrial division and degrade malfunctioning ones. Mitochondria, in turn, streamlined their genomes, surrendering autonomy for stability. What remained was a partnership built on trust and constant surveillance. The modern cell still carries traces of that evolutionary diplomacy, with molecular checkpoints that monitor mitochondrial health and trigger self-destruction if cooperation breaks down. For all its elegance, this arrangement remains mysterious. Why did this particular partnership succeed when so many others must have failed? We know that similar symbioses exist even today, bacteria living inside other cells, sometimes beneficial, sometimes parasitic. But the eukaryotic merger was unique in its permanence. Perhaps it worked because oxygen metabolism was simply too useful to give up, or perhaps the host cell lacked the enzymes to destroy its guest, forcing coexistence until chemistry forged compatibility. Either way, what began as accident evolved into structure. Genetic analyses have helped us trace the lineage of this event. The host appears to have belonged to a branch of archaea related to a group now called Asgard archaea, microbes found in deep marine sediments that show surprising complexity for their kind. Their membranes form flexible protrusions capable of engulfing particles, a trait that might have made symbiosis possible. The captured bacterium, on the other hand, seems to have come from the alpha proteobacteria, relatives of modern rickettsia, intracellular parasites that invade host cells even today. If this reconstruction is correct, then the origin of complex life was born not from harmony, but from predation that turned into dependence. The implications of this union are staggering. Before it, single cells were limited by surface area, how much energy their membranes could capture or exchange. A mitochondrion, by internalizing that membrane surface, solved the problem. Instead of one energy harvesting layer, the cell now had thousands folded within each organelle. This expansion of energetic capacity allowed genomes to grow, proteins to diversify, and regulatory systems to bloom. Complexity was no longer expensive, it was subsidized by oxygen. The cell could now afford curiosity. In this light, the rise of eukaryotes wasn't simply another evolutionary step, it was the moment life learned to delegate. The mitochondrion took over the burdensome task of energy generation, freeing the host to explore innovation elsewhere. Specialization emerged for the first time. Yet, at its heart, the system remained a union of equals, each dependent on the other's survival. A eukaryotic cell is, in the most literal sense, a conversation between two ancient genomes, still continuing after 2 billion years. We can see echoes of that dialogue in every heartbeat and breath. When oxygen enters your lungs and is ferried to your cells, it's mitochondria that take it in, splitting molecules and releasing energy that powers thought, movement, and memory. Every flicker of consciousness is sustained by an organelle that began as a foreign invader. The irony is profound. Our vitality comes from a domesticated parasite. Without that ancient act of restraint, that single instance where digestion paused, there would be no complex life, no plants, no animals, no us. Of course, much remains uncertain. The fossil record from this period is sparse, and the molecular traces are buried under billions of years of evolution. We can reconstruct only fragments: the genetic mosaics in modern cells, the biochemical similarities between mitochondria and their bacterial cousins, the signatures of oxygen metabolism preserved in ancient rocks. Yet each line of evidence points to the same conclusion, that the merging of two cells created something fundamentally new. If there is a lesson in this, it may be that life advances not just by competition, but by cooperation at improbable scales. Symbiosis, far from being a rare exception, may be evolution's most creative force. When boundaries meet and don't dissolve, when two systems choose negotiation over annihilation, something remarkable can emerge. In this case, it was the architecture of every living being larger than a microbe. The story of endosymbiosis is, in essence, the story of coexistence written into flesh. Two lineages that began as strangers learned to operate as one. Their communication so refined that separation became impossible. Even now, the mitochondria in your cells retain a whisper of that ancient independence. They divide on their own schedule, carry their own genes, and respond to the rhythms of energy as if remembering another life. Inside you, a billion-year-old partnership still endures, still exchanging signals, still keeping the lights on. How did individuality survive teamwork? Somewhere between 1.6 and 900 million years ago, the world entered one of its quietest yet most transformative eras. Life had learned to cooperate with itself, not metaphorically, but literally. The single cells that had ruled Earth for billions of years began to cluster, communicate, and coordinate. It was not the dramatic revolution of fire or oxygen, but a slow, deliberate negotiation. How to be many without losing the sense of one. The earliest Earth was full of solitary cells, resilient, clever, and self-contained. Each was a world unto itself, balancing internal chemistry against the chaos outside. They competed for nutrients, adapted to local conditions, and evolved in countless directions. But as oxygen spread and resources fluctuated, the world began to favour collaboration. Clustering provided safety. It allowed cells to share tasks, buffer against change, and collectively modify their surroundings. In the language of signal weighting, cooperation meant amplifying beneficial signals, chemical cues that favoured collective survival, while suppressing those that led to isolation or collapse. The first steps toward multicellularity were probably reversible. Many modern microbes still form temporary colonies, joining and separating as conditions demand. Cyanobacteria, for instance, can form filaments where some cells specialize in photosynthesis, while others fix nitrogen, each relying on the other's products. This is cooperation through division of labor, an ancient strategy that predates true multicellularity. It shows that specialization, the ability to perform one role well instead of many poorly, is one of life's most powerful evolutionary inventions. In those ancient seas, communication was chemical. Cells released and detected small molecules in their environment, a process scientists today call quorum sensing. When enough individuals signaled the same way, the collective behavior changed. Genes turned on or off, new molecules were produced, and the group acted as one. This ability to sense density and respond collectively was the molecular seed of society. It meant that a cell's behavior was no longer determined solely by its internal state, but by the state of its community. The boundaries between self and other began to blur. Gradually, some clusters of cells evolved permanent bonds. Instead of drifting apart after cooperation, they stayed together, dividing in sync and inheriting their adhesion traits. The geometry of these clusters mattered. Sheets, filaments, and spheres all offered different balances of communication and resource sharing. Flat colonies allowed cells to share signals easily but limited growth. Spherical ones protected inner cells but created challenges for feeding. Nature experimented endlessly, refining the architectures of cooperation until some configurations became self-sustaining, the earliest true multicellular organisms. Fossil evidence from this era is sparse but suggestive. In rocks over 1 billion years old, we find microscopic impressions of spherical colonies, some resembling modern algae or simple protozoans. These fossils, like Banyomorpha and Grippania, show patterns of organized growth, suggesting that their cells communicated and divided according to shared rules. Such coordination required more than physical contact. It needed regulation, timing, and feedback, the hallmarks of internal signaling networks. Inside these colonies, individuality didn't vanish, it was repurposed. Cells still followed their own biochemistry, but within a new hierarchy. Each cell's local decisions contributed to the whole, and the collective stability fed back to shape the fates of individual members. It was a form of distributed intelligence, not consciousness, but a primitive awareness of context. Cells began to specialize permanently. Some took on reproductive roles, others handled metabolism or structure. For the first time, death and sacrifice gained evolutionary value. A cell could die for the good of the organism, and its genes would still be passed on through the whole. This was a radical shift in the logic of survival. For billions of years, evolution favored selfishness, replication at all costs. Now, new selective pressures rewarded cooperation, restraint, and communication. The measure of success became not how well a single cell survived, but how effectively it contributed to a greater, more stable pattern. Complexity arose not from competition alone, but from integration, from systems that could balance independence with interdependence. To sustain this balance, life needed a new kind of signal weighting, not between molecules within a single cell, but between cells in a group. Chemical gradients became the language of development. When one cell released a molecule, its neighbours responded differently depending on distance and concentration. From such simple rules, patterns emerged, stripes, layers, and axes that prefigured the body plans of future organisms. The geometry of cooperation literally sculpted form from feedback. We can still see these principles at work today in living systems. When slime moulds aggregate under stress, thousands of individuals crawl together, guided by pulses of a signaling molecule called cyclic AMP. Once united, they form a stalk and spore body, a temporary multicellular entity. Each cell must decide whether to contribute to the structure or to remain as a spore. Those that form the stalk die, sacrificing themselves so that others may disperse. It is evolution's first moral dilemma written in chemistry. The same pattern echoes later in the development of embryos, cells following gradients, interpreting signals, and choosing fates that serve the whole. For multicellularity to succeed, cooperation had to become encoded, literally. Genes controlling adhesion, signaling and regulation evolved to lock teamwork into inheritance. No longer could a single cell easily defect from the collective. Its survival now depended on others. But evolution never loses its memory. Even in the most complex multicellular organisms, echoes of this microbial negotiation remain. Our immune systems, for example, still operate through chemical quorum sensing, balancing activation and restraint to protect the whole body. Tumours, in contrast, are what happens when individual cells forget their membership in the collective and return to the ancient logic of unchecked replication. Cooperation, it seems, must always be maintained. Between 1.5 and 1 billion years ago, this cooperative architecture became the norm for many lineages. Algae, fungi, and protozoans all experimented with multicellular organization. The deep oceans, once ruled by solitary microbes, now hosted colonies large enough to be visible to the naked eye. Life began to shape its environment at new scales, forming microbial mats, reefs, and planktonic networks that changed how nutrients cycled through the seas. The planet's biogeochemistry, already transformed by oxygen, now entered another feedback loop, one dominated by cooperation. We often think of multicellularity as inevitable, but it likely evolved many times independently and under different pressures. Some lineages did it for protection, others for efficiency, and still others by accident when daughter cells failed to separate after division. Most experiments failed, collapsing under their own complexity. Only a few managed to stabilize communication long enough to build lasting forms. The fact that multicellularity arose repeatedly suggests it was not a miracle, but a natural outcome of life's tendency to seek stability through feedback. This period also introduced something subtle, but profound: the beginning of internal hierarchy. Once cells began to coordinate, some inevitably took control. Master regulators, signaling hubs that influenced others, evolved, giving rise to primitive forms of governance. The architecture of life started to resemble a fractal. Smaller autonomous units embedded within larger cooperative ones, each level influencing and constraining the others. The pattern is still visible today, from tissues to ecosystems. Life organizes itself through nested negotiations, but the success of these systems depended on balance. Too little communication, and the organism fell apart. Too much, and individuality vanished, leaving the system rigid and fragile. The sweet spot lay in partial autonomy, enough freedom for local adaptation, enough coordination for collective purpose. It's the same balance that governs everything from ant colonies to human societies. Evolution found that cooperation was most powerful when it preserved individuality within structure. When we look back at this long, unrecorded era, we see not the dramatic flourish of fossils or explosions of diversity, but the quiet evolution of connection. The ocean became a network of networks, clusters of cells whispering across gradients, deciding collectively how to grow, when to divide, and when to die. Geometry met communication, and from that marriage arose complexity. In a sense, multicellularity was life's first great architectural project. The shapes that emerged, filaments, spheres, layered colonies, were blueprints for everything that followed. They show that structure is not imposed from above but arises from interaction below. Each pattern of cooperation, each chemical signal, each weighted decision between cells was a prototype for the tissues, organs and bodies that would later evolve. The geometry of cooperation is, in essence, the geometry of all living things. Even now, inside you, trillions of cells maintain this ancient covenant. They communicate constantly through chemical messengers, responding to needs larger than their own. Every heartbeat, every breath, every moment of thought is a product of that quiet symphony, first composed 1 billion years ago by cells learning to live together. Life discovered that survival is not just about being alone, but about belonging, about finding harmony between self and system. Before brains, could colonies of cells already feel? Around 800 million years ago, the planet was stirring again. Ice had wrapped itself around much of the Earth during the long cryogenian freezes, but beneath that frozen shell, life continued, quietly reorganizing, learning new ways to sense, react, and coordinate. The multicellular experiments of earlier ages were now more than loose clusters of cells. They pulsed, flexed, and contracted in unison, hinting at something remarkable. Tissues communicating across distance, sharing signals faster than chemistry alone could allow. Before there were nerves, there were electrical whispers. To understand how this began, we have to strip away our idea of the nervous system as a single invention. Nerves were not created from nothing. They were refined from ancient tools every cell already carried, ways to manage charge, to move ions, and to respond to changes in their environment. Long before neurons existed, the membranes of single cells could feel the world through electricity. Proteins embedded in those membranes acted as tiny gates, opening and closing in response to voltage or chemicals, allowing sodium, potassium or calcium ions to flow in and out. Each movement altered the cell's potential, creating fleeting electrical differences that could trigger reactions. It was not thought. It was physics translated into biology. These voltage changes, called action potentials in their modern form, were first just local phenomena, one cell's internal adjustment to its surroundings. But in colonial organisms, something extraordinary happened. The charge from one cell could spread to its neighbours. As membranes touched and fused, the signal leapt across junctions, rippling through tissues like a wave. Electrical coordination, not yet organised into nerves, began to synchronise movement. This was the embryo of sensation, not yet a mind, but a body learning to respond as one. The fossils from this time are sparse, but molecular evidence offers clues. The genes that build ion channels, the proteins that let cells send and receive electrical signals, are ancient, far older than animals themselves. Even sponges and single-celled relatives of animals possess versions of these genes. That means the potential for bioelectric communication predates the first neurons by hundreds of millions of years. Life was already wired for responsiveness long before it had brains. In the deep, cold oceans of the late Proterozoic, simple animals began to explore what this meant. Among them were the sponges, organisms so basic that they lack nerves, muscles or organs, yet still manage to coordinate their behaviour. A sponge can close its pores when disturbed, regulating water flow through its body. It does this through waves of electrical potential passing from cell to cell. No single cell knows what the whole is doing, but together they achieve coherence. The sponge is proof that communication can create coordination without hierarchy. Other early animals took this further. Cnidarians, the group that includes jellyfish, sea anemones and corals, developed true nerve nets. These were not centralized brains, but diffuse meshes of specialized cells capable of rapid signaling. When a jellyfish pulses through the water, its rhythm is guided by electrical activity spreading through this network. Each contraction is the result of thousands of cells sharing information about stretch, pressure, and flow. The jellyfish does not think, but it feels in a primitive mechanical way, a feedback loop of motion and sensation. At the molecular level, the rise of nerve nets was a triumph of chemistry's old themes: coupling, feedback, and reinforcement. The first neurons evolved from sensory and secretory cells, those that released molecules into their surroundings to influence others. Over time, the distances between communicating cells shortened, and specialized junctions called synapses evolved to speed up exchange. Instead of leaking signals into the open water, cells began to whisper directly to their neighbours through targeted release of neurotransmitters. The gap between them, the synaptic cleft, was narrow, just enough to keep the system precise and efficient. This change was monumental. Information that once drifted slowly as chemical gradients could now move almost instantly as voltage pulses. Coordination became possible on a new scale. The result was not intelligence in the modern sense, but reactivity, a living body that could sense its environment and respond coherently. For the first time, the ocean hosted creatures that could swim, feel touch, and adjust their behaviour dynamically. They were not conscious, but they were aware in the simplest way a system can be aware, by integrating information. The emergence of these nerve nets paralleled another revolution, the development of muscle. Movement and sensation evolved together, two sides of the same electrical coin. A signal that triggered contraction in one cell could now propagate through tissue, producing waves of motion. Light, pressure, and chemical gradients could all serve as stimuli, translated into electric messages that produced coordinated response. The nervous system was, in essence, a new language of physics within biology, a way for matter to translate external change into internal order. At this stage, the diversity of forms was astonishing. Some early animals, like comb jellies, developed unique neural architectures entirely separate from those of cnidarians, suggesting that the nervous system may have evolved more than once. Others, like placozoans, flat, simple animals with no real tissues, displayed coordinated movement without nerves, relying on direct contact and chemical signalling. It seems that life was experimenting with the geometry of awareness, testing how much complexity could emerge from connectivity alone. What unites all these forms is the principle of signal weighting. In a multicellular organism, not every cell's input can be treated equally. Some signals must be amplified, others ignored. This required the evolution of thresholds, mechanisms to decide when a stimulus was strong enough to matter. The earliest neurons were probably threshold detectors, firing only when the combined input from many sources reached a critical point, In this way, they filtered noise into meaning. It was the same logic that once governed chemical reactions in the prebiotic world, now expressed in living tissue. The ocean itself became a nervous planet. Electrical currents, light pulses, and chemical gradients intertwined as networks within networks. Jellyfish drifted through water that flickered with bioluminescence, light used for signalling, mating, or defense. Coral colonies communicated across surfaces, coordinating feeding and reproduction. Even microbes, long before animals, used electrical pulses to organize within biofilms. It is tempting to think of Earth's biosphere at this stage as one vast distributed sensory organ, a planet beginning to perceive itself through the chemistry of its inhabitants. Still, we must resist the urge to romanticize. These systems were fragile and primitive. They processed information without awareness, acting purely on feedback. But feedback itself was revolutionary. It allowed behavior, something life had never truly possessed before. An organism could now do more than endure. It could choose between alternatives, however simple those choices were. Move toward light, contract when touched, feed when signals align. In these micro-decisions lay the first glimmers of agency. By 550 million years ago, nerve nets had become a defining feature of the animal kingdom. Sponges remained as reminders of the pre-neural past, while cnidarians and comb jellies explored the frontier of sensation. The ocean, once filled with passive drifters, now hosted organisms that reacted, coordinated, and even hunted. The feedback between environment and life intensified. Predation, avoidance, and adaptation entered the stage. The ability to feel, however dimly, was transforming evolution itself. And yet, even as these creatures pulsed and swam through ancient seas, their simplicity remained deceptive. Beneath every movement was a profound continuity with everything that had come before. The ion channels that fired in a jellyfish's nerve net were the same kind of gates that had once managed chemistry in solitary cells billions of years earlier. The electrical gradients that now pulsed through tissues were the descendants of the same gradients that had powered protocells at hydrothermal vents. Life was not inventing new principles. It was amplifying old ones, giving them geometry, depth, and rhythm. It's humbling to realize that the feeling of touch, the perception of motion, even the ability to think, are extensions of this ancient system. Every neuron in your body carries the memory of that era, using the same ions, the same electrical rules to transmit information. The nervous planet never disappeared. It simply folded into us. Our brains are not separate from the biosphere's original communication network. They are its latest, most intricate expression. Before brains, life could already feel, not with emotion, not with thought, but with sensitivity to the changing world. The first nerve nets were not the beginning of consciousness, but the beginning of connection, an electrical web linking cell to cell, body to environment, and life to planet. The Earth itself, once only reactive, had learned to sense its own rhythms through the beings it produced. Why did evolution suddenly turn the volume up? Around 541 million years ago, the silence of Earth's ancient seas broke. For nearly 3 billion years, life had evolved quietly, cells merging, cooperating, and sensing in slow motion beneath the waves. Then, within what seems like the blink of geological time, the ocean exploded with movement, form, and light. Eyes appeared, armor appeared, predators and prey began a feedback loop that would never stop. This was not just a diversification of bodies, it was a surge of information, an escalation in how life sensed, processed, and responded to the world. It was as if the planet itself had learned how to notice. Before this event, the seas had been populated by simple, soft-bodied creatures. They filtered, crawled, and drifted, following chemical gradients and light without urgency. But by the dawn of the Cambrian period, something changed. Fossil beds like the Burgess Shale in Canada and Xinjiang in China preserve the moment vividly. A riot of new anatomies, new strategies, and new ways of perceiving. Creatures with eyes, shells, claws, and spines appeared seemingly overnight in the geological record. Behind that apparent explosion was not magic, but a network of reinforcing causes: genetics, ecology, and most of all, communication. When paleontologists speak of the Cambrian explosion, they often emphasize the rapid diversification of body plans, what biologists call phyla. But beneath that morphological diversity lay a deeper evolution, the escalation of signal systems. Organisms began to compete not only for food or space, but for information. Who could detect danger first? Who could hide better? Who could track motion, light, or vibration most efficiently? Evolution had always been about survival, but now it became about perception. The invention of the eye was central to this transformation. The first eyes were not complex orbs like ours, but simple, light-sensitive patches, clusters of cells containing photopigments that reacted to brightness. These patches evolved into shallow cups, improving directionality, and eventually into lenses capable of focusing images. With sight came a new kind of feedback loop. Predators who could detect prey shapes rather than mere shadows gained an enormous advantage. Prey, in turn, evolved transparency, armor, and camouflage. Each adaptation forced the other to improve, driving an evolutionary arms race measured not in strength, but in perception. Trilobites, with their intricate compound eyes, are among the most iconic symbols of this age. Their eyes were built from calcite crystals, each functioning as a lens, a marvel of optical precision that predates vertebrate eyes by tens of millions of years. These ancient arthropods could see across the seafloor in mosaic-like patterns of light, detecting movement and structure in ways no organism before them could. In their vision, the world became textured, detailed, and suddenly urgent. The oceans had turned into a landscape of pursuit and evasion, guided by light. The Cambrian explosion was also an explosion of behavior. For the first time, animals dug into sediments, built burrows, and actively modified their environments. This agitation of the seafloor left behind trace fossils, networks of tunnels and feeding tracks, marking the rise of intent and exploration. Movement was no longer random, it was guided. Muscles coordinated through nerve nets became engines of strategy. To move with purpose, an organism had to integrate multiple signals: touch, chemical cues, light, into a single decision. That integration was the essence of a nervous system maturing. One hypothesis for why this all happened so rapidly points to oxygen. The Great Oxidation event had long passed, but by the Cambrian, oxygen levels had climbed high enough to support energetic metabolisms. Complex tissues like muscles and sensory organs require high energy throughput, and mitochondria, those ancient bacterial symbionts, could finally supply it. Energy and information are partners in evolution. One fuels the other. When energy availability increased, so did the capacity for neural complexity and behavioral experimentation. Another force behind the Cambrian surge was ecological feedback. Every innovation created new pressures. The evolution of the first hard shells, for example, changed not only defense but also sensory ecology. A shell blocked light and sound. An organism encased in armor needed better internal sensors to interpret its surroundings. Thus, touch-sensitive bristles and vibration-detecting organs evolved. Likewise, the appearance of active swimming predators forced prey to detect fluid disturbances, leading to the rise of lateral line-like systems in early animals. Each sensory upgrade triggered another. It was an arms race not of violence but of information density. In the Precambrian world, organisms interacted through slow chemical diffusion. Now, electrical and optical communication dominated. Reaction times mattered. Neurons that could fire faster, integrate more inputs, and coordinate larger muscle groups had the upper hand. This selection pressure favoured the expansion of neural tissues, the specialisation of sensory cells, and the formation of small ganglia, clusters of neurons acting as primitive control centres. The brain, though not yet fully formed, was quietly on its way. The Cambrian explosion also transformed the evolutionary role of colour and light itself. As eyes improved, the ocean changed visually. Pigments that once served only for photosynthesis or protection against UV radiation gained new meaning as camouflage or display. Patterns evolved: stripes, spots, gradients, and the seas began to shimmer with communication coded in light. Even bioluminescence, possibly older than the explosion, took on new ecological functions. Organisms began to use light as signal, to attract mates, confuse predators, or coordinate movement. The very physics of vision became a new evolutionary language. In this sense, the Cambrian was less a burst of complexity than a burst of awareness. Information began to loop through biology in unprecedented ways. A trilobite's sensing motion altered its behaviour, which altered the behaviour of its prey, which altered the behaviour of its prey's prey. The ecosystem itself became a feedback network of perception, the first global web of nervous interactions. For the first time in Earth's history, animals weren't just alive, they were aware of one another. The geological record supports this transition. In Cambrian strata, we see the rise of trace fossils, the marks of motion suddenly growing deeper and more complex. Burrows twist and branch like signatures of curiosity. Trackways across ancient seafloors reveal directional intent, sometimes even pursuit. These patterns imply nervous systems capable of integrating memory, stimulus, and motion. They are the footprints of minds still forming, learning to navigate a world that had become unpredictable. And yet, the Cambrian was not an explosion in the human sense of speed. It unfolded over tens of millions of years, still rapid by geological standards, but slow enough for feedback loops to entrench themselves. The apparent suddenness we see in the fossil record is partly an illusion of preservation. Hard parts fossilize, soft ones do not. Once creatures began building shells and exoskeletons, they began leaving better evidence of themselves. Evolution had not accelerated overnight. It had reached a threshold of visibility. Another element was genetic potential. By the time of the Cambrian, the molecular toolkit for building complex bodies, the so-called Hox genes and developmental regulators, was already in place. These genes act like architects, directing where limbs, eyes, and organs should form. Once environmental conditions and ecological pressures aligned, these latent instructions could be expressed in myriad combinations. The result was a cascade of novelty, all built from the same genetic alphabet. The explosion, then, was as much informational as anatomical, a new way of recombining existing codes. The Cambrian oceans must have been dazzling. Imagine standing on the seabed beneath shallow sunlight, watching translucent creatures swim through beams of blue and green. Trilobites scuttled across rippled sand, their compound eyes gleaming. Soft-bodied predators like Anomalocaris drifted with undulating grace, scanning for motion with eyes made of thousands of lenses. Worms burrowed and tunneled, stirring sediment clouds that shimmered in the light. Every flicker, every shadow, every vibration carried meaning. The ocean had become a field of signals, a dense network of feedbacks humming with competition and awareness. But even amid all this innovation, the logic remained ancient. Life was still optimizing signal weighting, deciding what to pay attention to and what to ignore. Evolution had simply expanded the bandwidth. The transition from chemical to electrical to optical communication had reached its apex. The planet had gone from a world that sensed heat and flow to one that saw, hunted, and hid. It was not consciousness yet, but it was a rehearsal for it. A billion nervous systems testing how far awareness could go. By the end of the Cambrian, the rules of life had changed forever. Survival no longer depended solely on metabolism or reproduction, but on perception and reaction time. The age of sight had begun, and with it, the quiet world of the Proterozoic ended. Life had turned up the volume, and the planet would never be silent again. How did organisms start archiving experience in bodies? Around 500 million years ago, life took another quiet leap, this time inward. After the Cambrian burst of eyes, limbs, and reflexes, evolution began to refine how those signals were stored, not just sensed. The ocean was now full of awareness, but awareness without memory is only noise. To survive, creatures needed not only to feel, but to remember what they felt. The age of skeletons, senses, and storage had begun. The first step toward memory was stability. Soft tissues alone could not sustain complex behavior. They decayed too easily, both in the fossil record and in real time. So evolution started building frameworks, skeletons, exoskeletons, and cartilage, to anchor both motion and sensation. This structural reinforcement wasn't just mechanical, it provided architecture for nerves. As bodies stiffened, Neurons could be positioned precisely, sensory organs could anchor reliably, and the signals travelling through those new frameworks became faster and more coordinated. Form and information co-evolved, locked in feedback. In early marine vertebrates, the jawless fish of the Ordovician and Silurian periods, we begin to see this marriage of structure and signal. Their internal skeletons of cartilage housed the first spinal cords recognizable as such. Neurons were no longer scattered like diffuse nets across the body. They were centralized, bundled into longitudinal cables that carried information between head and tail. The nervous system had discovered geometry. A central line of communication was more efficient than a web. It allowed for reflex arcs, direct connections between sensory input and motor output, reducing reaction time dramatically. This centralization also created the possibility of a hierarchy within the nervous system. Some neurons could now specialize in processing raw data, while others coordinated movement, and still others acted as integrators, comparing past and present stimuli. For the first time, information could linger within an organism, stored chemically, even if only for seconds. It was the beginning of biological memory, the capacity to compare now with then. At the microscopic level, the chemistry of remembering was astonishingly elegant. Each synapse, the gap between neurons, was not a fixed connection, but a dynamic one. When two neurons fired together repeatedly, the connection between them strengthened. When they didn't, it weakened. This phenomenon, known today as synaptic plasticity, became the foundation for learning. It allowed patterns of experience to modify the structure of the nervous system itself. In simple animals like lampreys and early fish, these processes were already underway. Their behavior showed traces of learning, avoidance, recognition, even rudimentary conditioning. The ocean had begun to think, if only in reflex. But storing information required energy, and the nervous system is an energy-hungry machine. To sustain its expansion, evolution needed new efficiency tricks. One of the most important was the invention of myelin, a fatty sheath that wraps around nerve fibers, insulating them and allowing electrical signals to travel faster. Myelination was like upgrading biological wiring from copper to fiber optics. It let signals leap from node to node rather than creep continuously, speeding transmission by orders of magnitude. With myelin, reaction and coordination became not just possible but fluid. Creatures could swim, turn and strike with precision. At the same time, the evolution of sensory systems became deeply integrated with skeletal changes. Hard parts like bone and cartilage provided leverage, but they also offered protection and resonance. The first internal ears, for instance, emerged as fluid-filled chambers that detected vibrations, repurposed from balance organs. Eyes became more complex, focusing light onto retinas capable of detailed image formation. Pressure sensors along the sides of fish, the lateral line systems detected movement in the surrounding water, a kind of touch at a distance. Each new sense brought new neural circuits to interpret it, and each circuit layered more meaning onto the world. The interplay between skeleton and sensation created something profound. Bodies that could model their environment. A fish navigating through a coral maze or avoiding a predator's shadow was doing more than reacting. It was computing, comparing memory traces to current input. These comparisons required specialized neurons, ones that integrated multiple sensory streams into cohesive responses. The brainstem and forebrain of early vertebrates began to take shape, regions dedicated not just to reflexes, but to pattern recognition. Memory itself, however, is fragile. Chemical gradients fade, synaptic weights decay, and signals are noisy. The nervous system solved this through redundancy and reinforcement. Multiple pathways carried similar information, and the repetition of patterns, such as swimming rhythms or hunting motions, helped ingrain them. Some neuroscientists suspect that the rhythmic swimming of early fish may have served as a natural rehearsal mechanism, consolidating motor memory much like modern animals practice behaviors in sleep. Whether or not that's true, movement and memory were now inseparable. Every flick of a fin carried echoes of past success. The skeleton, meanwhile, did something even stranger. It became a recorder of experience. Bones don't just provide support, they reflect stress and use. The microscopic growth rings in ancient fish bones tell us that their bodies archived the rhythms of life, seasonal migrations, periods of hunger, and bursts of activity. In a literal sense, their bodies were storing the memory of their environment. Life had found a way to write its own history into its own frame. As nervous systems centralized, so too did behavior. By the Devonian period, roughly 400 million years ago, vertebrates like placoderms and early bony fish displayed sophisticated interactions. They hunted in structured ways, guarded territories, and possibly even engaged in primitive social behavior. To do that, they needed more than reflexes. They needed circuits that could anticipate. Anticipation is the beginning of prediction, and prediction is the seed of what we later call thought. Still, we should resist the temptation to see inevitability here. Many lineages never evolved central nervous systems or bones and yet thrived. The jellyfish continued to drift, the worms to burrow, the corals to build reefs. Complexity is not destiny. It's one option among many. But for those that took it, the trade-off was immense. Centralized nervous systems required continuous maintenance, precise ion balances, and vast energy supplies. In exchange, they gained a new kind of power, flexibility. The first fish with true brains could modify their behavior within a lifetime. They could learn to associate patterns, to remember safe routes or dangerous predators. Their memories were fleeting compared to ours, perhaps lasting minutes or hours, but they marked a transition from evolution as the only teacher to experience as a teacher too. The ocean had become an archive of learned responses. Information was no longer just encoded in genes, it was being written in neural circuits. We can trace this through the fossil record, though indirectly. Endocasts, natural moulds of ancient brain cases, reveal the gradual enlargement of sensory and motor regions over time. The optic lobes grew as eyes improved. The cerebellum expanded as movement became more complex. The spinal cord thickened, reflecting increased signal traffic between body and brain. Each anatomical refinement represented another layer of integration, a new way to weight signals, filter noise, and preserve meaning. At the molecular level, the same principles apply to this day. The neurotransmitters used by those early fish, glutamate for excitation, GABA for inhibition, dopamine for reward, are still the molecules that shape our memories and emotions. When you remember a face or a melody, you're using chemical pathways older than bones. Evolution doesn't replace, it repurposes. The neurons that first allowed a Silurian fish to learn from a mistake are your ancestors' neurons, stretched across time. So how did organisms start archiving experience in bodies? By turning structure into story. Skeletons stored the record of stress. Neurons stored the record of experience. The two merged to create life forms that not only existed in the moment, but carried fragments of the past within them. The nervous system became the historian of the body, and the body became the library of life. This was the quiet revolution after the Cambrian's noise, the shift from reacting to remembering. It set the stage for everything that would follow: consciousness, emotion, planning, culture. But in the beginning, it was just a fish learning to swim a little smarter than it did the day before. The first archive wasn't made of stone or bone or silicon, it was made of salt water and electricity. Did brains evolve faster when gravity changed? Around 400 million years ago, life faced one of its strangest frontiers: dry land. For billions of years, the ocean had shaped every reflex, every eye, every nerve. The chemistry of thought itself had evolved in water, carried by ions of salt and the steady pressure of buoyancy. But as fins turned to limbs and gills gave way to lungs, evolution faced a new challenge: how to make a nervous system built for fluid survive in air. Every sense had to be rewritten, every signal had to be reweighted. It was not just the conquest of land, it was a neurological revolution. The first amphibious pioneers, creatures like Tiktaalik, Acanthostega, and Ichthyostega, didn't just adapt their bodies, they had to adapt their perception of space. In water, gravity is gentle. Movement is a matter of balance and thrust. On land, gravity became an unrelenting teacher. Each step demanded fine-tuned control over posture, coordination, and equilibrium. The vestibular system, once useful for orientation in water, now had to interpret a new direction of constant pull. The brain began to integrate feedback from muscles, joints, and the inner ear to maintain balance against gravity's persistent tug. The shift in physics forced a shift in thinking. The transition to land also transformed how animals saw and heard. Underwater, sound travels faster and farther, and vision operates in a muted, filtered spectrum. In air, those dynamics change dramatically. Early tetrapods had to rewire their sensory systems to make sense of a noisier, brighter world. The eyes moved forward on the head, lifted higher for scanning horizons rather than murky depths. The skull flattened, improving stereoscopic vision. For the first time, depth perception meant survival, a necessary tool for hunting or avoiding predators on uneven ground. Hearing was another frontier. Ears evolved from gill arches, gradually repurposed to detect air vibrations instead of water pressure. The stapes, a small bone once part of the fish jaw, became a conduit for sound, the ancestor of our middle ear. Yet early terrestrial ears were primitive. They likely sensed only low-frequency vibrations, enough to detect footsteps or rustling leaves. Still, that simple awareness marked a new kind of sensitivity. The world now spoke through air. Smell, too, gained importance. In water, chemical cues are diluted and diffuse. On land, they are concentrated, ephemeral, carried by currents of air. The olfactory system of early amphibians expanded, with neurons dedicated to detecting a wider range of volatile molecules. Smell became the bridge between distance and detail, a way to sense invisible presences beyond immediate reach. For a creature crawling onto a muddy shoreline, scent offered the first true map of land, one drawn not in light, but in molecules. What this means is that the brain was not simply evolving new organs, it was reorganizing its sensory geography. Neural maps, the spatial arrangements of sensory inputs in the brain, began to stretch and specialize. The forebrain, which handled smell and complex integration, grew larger. The cerebellum, crucial for coordination, became more refined. Meanwhile, parts of the midbrain responsible for vision and movement synchronization thickened, linking perception directly to action. The result was a more layered architecture, not a larger brain yet, but a smarter one. The fossil record gives subtle glimpses of these transitions. In endocasts, the internal impressions of ancient skulls, we can see expanded olfactory bulbs in early tetrapods and pronounced midbrain lobes. The bones around the ear show widening cavities, accommodating air-filled chambers that could amplify sound. And the limb bones tell the story of control, wrist-like joints, digits, and muscle attachments designed for weight-bearing and maneuvering. Each skeletal change reflects a neural one, as the brain learned to predict and stabilize movement in a gravity-dominated world. It's easy to overlook how radical that was. In the ocean, inertia and water resistance smooth out mistakes. A slight twitch of a fin is buffered by the medium around it. On land, errors are punished instantly. Fall, and bones break. Miss a step and a predator catches you. Evolution rewarded not brute strength but coordination, timing, and sensory integration. In that sense, gravity may have been the first true sculptor of intelligence. Some neuroscientists suggest that the cognitive leap from water to land didn't just refine the senses, it laid the foundation for predictive processing, the brain's ability to model future states. On unstable terrain, an animal must anticipate the next movement before it happens. Muscles prepare for pressure before the foot lands, eyes adjust before the body turns. This continuous forecasting required a new internal rhythm, a sense of what comes next. The early land brain was not only reacting but rehearsing, turning perception into expectation. The environment itself changed the flow of signals. Light on land is more variable, shifting with clouds, shadows, and the angle of the sun. Temperature fluctuates between day and night. Smells drift and disappear. To survive, organisms needed to prioritize, to decide what mattered. The principle of signal weighting became ever more sophisticated. Background noise had to be filtered out so that only critical cues triggered action. That required new inhibitory circuits, neural systems designed not to act, to suppress irrelevant signals. Evolution discovered attention. By the late Devonian and Carboniferous periods, amphibians had given rise to the first true terrestrial vertebrates. early reptiles. Their brains reveal another innovation: increased compartmentalization. Specific regions began taking ownership of distinct functions: vision, olfaction, motor control. This modularity allowed greater specialization without losing integration. In a sense, the brain was becoming a federation of experts, each tuned to its own sensory domain, yet constantly in conversation with the others. Interestingly, the energy cost of all this was enormous. On land, animals could not rely on constant dissolved oxygen from water. They needed lungs and more efficient circulatory systems to keep the brain fed. This led to tighter coupling between respiration, circulation, and neural demand. Even breathing became part of cognition, rhythmic, patterned, and linked to attention. When you take a breath today and focus your mind, you're echoing a feedback loop perfected hundreds of millions of years ago in swamps and floodplains. The evolution of the spinal cord also mirrored this new reality. Once a simple relay between brain and body, it began to host local circuits capable of reflexes and even rhythmic movements independent of direct command. These central pattern generators allowed walking or swimming motions to continue automatically once initiated. The brain became more of a conductor, less of a micromanager, an efficient adaptation to the demands of terrestrial locomotion. Fossilized trackways from this period capture the story in motion. The footprints of early tetrapods crossing mudflats show careful gait adjustments, each print placed with precision. These were not random flailing creatures, but deliberate movers, guided by feedback from touch and pressure. The coordination required was immense. Every step was a neural symphony. Muscles balancing against gravity, eyes scanning for obstacles, vestibular sensors tracking tilt, and memory recalling stable paths. Walking was, in effect, one of the first cognitive acts. The neural complexity needed for life on land also transformed sleep and rest. Underwater, animals could drift or float in safety. On land, stillness was dangerous. To remain motionless for long required vigilant systems that could partially deactivate the body while keeping sensory awareness. Some scientists speculate that early forms of unihemispheric sleep, where one half of the brain rests while the other monitors, may trace back to this time. Even in rest, life was adapting to the unpredictability of the new world. Over millions of years, these innovations stabilized into the blueprint we still carry. A brain divided between fast reflex and slow prediction, between movement and thought. The amphibians and reptiles of the late Paleozoic did not think like mammals, but their brains already reflected the principles of modern intelligence: integration, attention, and anticipation. When gravity changed, life didn't just grow legs, it grew foresight. And yet, even with all this complexity, the underlying principle remained beautifully simple. The same feedback loops that once balanced chemical gradients in the earlier cells were now balancing bodies in motion. The same ionic flows that once pulsed through membranes at hydrothermal vents now flickered through neurons, guiding movement across dry land. Life's intelligence had always been about feedback, about listening to its own signals and adjusting accordingly. The planet had not just filled with new creatures, it had filled with new ways of perceiving itself. The story of the brain meeting the land is, at its core, a story of translation, translating water logic into air logic, translating buoyancy into balance, translating reflex into anticipation. It was evolution's great act of sensory reprogramming. Every step, every breath, every vibration of sound through air carried data that the brain had to learn to interpret anew. And through that reinterpretation, life grew wiser. So did brains evolve faster when gravity changed? Perhaps not faster, but differently. They became architects of expectation, and that shift, from reacting to predicting, would echo through the ages, shaping how every living creature after would sense, move, and eventually think. How did darkness shape intelligence? Between 250 and 150 million years ago, while the world above filled with thunder lizards and daylight predators, another kind of evolution was unfolding quietly in the dark. It was not about muscle, size, or speed, but about timing, rhythm, and the subtle art of seeing when light was gone. Long after the first vertebrates conquered land, their descendants began learning the deeper pattern of the planet, that life did not just move through space, but through cycles of light and shadow. Nightfall became the next great frontier for the brain. The Mesozoic world, the so-called Age of Reptiles, was a theatre of light by day and an orchestra of signals by night. Dinosaurs dominated the sunlight hours, but as dusk settled over Triassic swamps and Jurassic forests, smaller, more secretive creatures emerged from the undergrowth. Among them were the ancestors of mammals, shrew-sized beings with fine fur and wide pupils, listening more than they saw. They lived under pressure from predators, yet in their caution, evolution found creativity. To survive in darkness, their senses and brains began to change. Night vision was not invented from scratch. The vertebrate eye was already a masterpiece of optical engineering, but adapting it for darkness required recalibration. In dim light, photon scarcity makes precision meaningless. What matters is sensitivity. So the eyes of nocturnal animals expanded, the corneas widened, the lenses thickened, and the retinas filled with rod cells, photoreceptors capable of detecting even a few stray photons. The price of this sensitivity was colour. Rods see in monochrome. But in return, life gained the ability to navigate the unseen. The world of the night was grey-scale, yet full of information. Movement, contrast, shimmer. The early mammals that scurried through the shadows of the Mesozoic evolved eyes that emphasized this trade-off. Their pupils became round and adjustable, their optics tuned for twilight. Behind the retina, a layer called the tapetum lucidum developed in some lineages, a reflective surface that bounced light back through the photoreceptors, giving each photon a second chance to be caught. When you see a cat's eyes glow in the dark today, you're seeing an echo of that ancient innovation. The mammalian lineage survived not by overpowering dinosaurs, but by outseeing them in darkness. But darkness also redefined how information was processed. Vision alone could no longer dominate perception. The night belonged to hearing and smell. The middle ear bones, originally part of the reptilian jaw, detached and shrank, becoming finely tuned levers that could detect subtle vibrations in air. High-frequency hearing, a hallmark of mammals, emerged. The world could now be mapped through sound, allowing small creatures to orient themselves even in total blackness. At the same time, the olfactory bulb, the brain's smell processing centre, expanded dramatically. Airborne scent, which carried meaning across time and distance, became a new form of memory. The night taught life to imagine what wasn't immediately visible. This sensory transformation rippled through the brain. The forebrain, where sensory integration occurred, grew proportionally larger in early mammals than in most reptiles. Neurons in the olfactory and auditory regions formed intricate networks capable of cross-referencing. A smell could trigger a memory, a sound could signal a pattern. In this way, the brain began constructing an internal world richer than the external one. The darkness demanded prediction and imagination, not mere reaction. Meanwhile, another subtler revolution unfolded inside every cell. The alternation between day and night, a pattern as old as the spinning of the planet itself, began to imprint itself in biology. The circadian rhythm, an internal clock that synchronizes physiology to the cycle of light and dark, became universal among animals. It is governed by molecular oscillators, feedback loops of genes that turn themselves on and off roughly every 24 hours. These loops regulate metabolism, hormone release, body temperature, and sleep. In essence, life internalized the rotation of Earth. Time itself became a biological signal. To live by light and dark required not just sensing the world, but anticipating it. The first creatures that could predict dusk or dawn had an enormous advantage. They could forage, hide, or rest before conditions changed. This ability to synchronize internal states with external cycles is one of the quiet triumphs of evolution. It allowed energy to be conserved, behavior to be coordinated, and neural systems to optimize performance. When the planet turned, the brain turned with it. For mammals, this synchronization carried emotional and cognitive consequences. The limbic system, the brain's emotional core, began to interlace with sensory and circadian inputs. Smell, sound, and memory fused with the rhythms of alertness and rest. Nightfall wasn't just a change in environment, it was a change in consciousness. In darkness, when vision faltered, the brain turned inward. Dreams in their earliest forms may have emerged from this interplay, the brain rehearsing sensory experiences in the absence of stimuli, a kind of internal simulation to keep circuits flexible. The night became both laboratory and refuge for thought. The fossil and anatomical record gives glimpses of this quiet revolution. The skulls of early mammals show enlarged olfactory bulbs and middle ears compared to their reptilian relatives. The orbital openings for eyes differ in shape, suggesting adaptation to low light. Even the tiny semicircular canals of the inner ear, responsible for balance, evolved to accommodate quick, agile movements in three-dimensional darkness. These creatures were not sluggish or primitive, they were athletes of the night. Reptiles, too, learned from darkness. Some lineages developed slit pupils, infrared-sensitive pits, and ultraviolet vision. The night was not only the mammal's domain, it was a shared evolutionary classroom, teaching multiple lineages the art of sensory economy. Each photon, each vibration, each molecule of scent became precious data. Evolution favoured creatures that could weight those signals appropriately, not overwhelmed by noise, not blind to detail, but tuned to the meaningful patterns of the dark. It's possible that the cognitive flexibility we associate with mammals today, curiosity, play, and memory, found its origins here in the rhythm of light and shadow. The constant alternation between perception and limitation trained brains to work with partial information. In darkness, every decision carried uncertainty, and uncertainty bred creativity. The mammalian brain became a machine for inference, not just reaction. An organ capable of guessing well when knowledge was incomplete. Even sleep itself, far from mere rest, evolved into a form of learning. During sleep, the brain replays neural patterns, consolidating memory and pruning noise. The cycles of slow wave and rapid eye movement sleep, first appearing in the early mammals, may have been byproducts of nocturnal adaptation, the brain simulating its sensory world in miniature to prepare for the next waking cycle. In that sense, darkness didn't just teach animals to see in low light, it taught them to imagine light when there was none. By the late Jurassic and into the Cretaceous, mammals remained mostly nocturnal, their survival strategy unchanged. But that long apprenticeship in the dark shaped them in lasting ways. Their hearing grew acute, their brains layered with complexity, and their sleep-wake cycles synchronized with cosmic precision. Even after dinosaurs vanished and daylight became safe again, their descendants kept the inner rhythm of night, a hidden clock still ticking behind the eyes of every human and animal today. Modern neuroscience confirms how deep this lineage runs. The human retina still contains specialized cells that respond not to images but to overall brightness, sending information directly to the brain's clock, the suprachiasmatic nucleus. Our hormones still rise and fall with the rhythm of the ancient day-night cycle. Melatonin, the molecule of sleep, is older than the first mammals. When you close your eyes at night and drift into dreams, you are participating in a biological ritual hundreds of millions of years old, one that began with tiny furred creatures listening to the dark. So how did darkness shape intelligence? By demanding foresight in the absence of sight, by teaching the brain to trust its memory, its smell, its imagination, by forcing life to keep time with the planet itself. The night was never the enemy of life, it was its mentor, the place where vision learned to dream, where the nervous system became an instrument not just of perception but of rhythm. Why did memory start depending on other memories? Between 120 and 10 million years ago, a new kind of intelligence began weaving itself through forests, plains, and skies. Not the solitary intelligence of a predator or the reactive wit of survival, but something collective. Mammals and birds had both emerged from ancient lineages shaped by the night and the rhythm of the planet. Now they were learning that awareness could be shared. Life was beginning to think together. The world at this time was unrecognizable compared to the dim ecosystems of the Mesozoic. After the great extinction that ended the age of dinosaurs, the Cenozoic opened with opportunity. Mammals diversified, filling every niche left vacant by the vanished giants. In the air, birds inherited the skies. Across continents, forests stretched and receded with climate shifts, creating patchworks of isolation and reunion. This constant flux demanded new strategies, and one of them was trust. For the first time, evolution began to favour minds that could model other minds. Survival was no longer just about what you remembered, but about how well you could remember the memories of others, who helped, who cheated, who warned you of danger, who shared food or hid it. Intelligence became social, and communication became memory's external hard drive. Among mammals, the first experiments in this new intelligence emerged in herding and group-living species: elephants, dolphins, primates, canids, and even some bats. Among birds, the same pattern appeared in corvids and parrots. Each group evolved independently, yet converged on similar solutions. They developed long-term relationships, complex vocalizations, and the ability to interpret gestures and tones. Cooperation began as simple coordination, keeping a flock aligned or warning others of predators. But over millions of years it turned into something richer, the sharing of attention itself. What allowed this transformation was not just behavior, but biology. Inside the brain, a new type of neuron appeared, one that fired both when an animal performed an action and when it observed another performing it. These so-called mirror neurons, first discovered in the motor cortex of monkeys, represent one of nature's quiet revolutions. They allowed individuals to understand others not by reasoning, but by feeling, to simulate another's behavior internally, to predict and empathize. When one bird saw another tilt its head to listen, or one dolphin watched another leap, its own neurons lit up in resonance. The mind had found a way to mirror the world. This mirroring opened the door to imitation, and imitation opened the door to culture. Young animals could now learn by watching rather than by trial and error. Birdsong is one of the clearest examples. In many species, the ability to sing correctly depends on early exposure to adult models. A young zebra finch listens, practices, and refines its song until it matches the pattern it heard, a form of vocal learning that parallels how human infants learn speech. But birds also innovate. Regional dialects arise, melodies shift, and individuals borrow phrases from their neighbours. A single song becomes both memory and conversation, a network of evolving information carried not in genes but in sound. In mammals, the same principle expressed itself through calls, gestures, and facial expressions. Primates developed distinct alarm calls for different predators. Dolphins invented signature whistles, unique acoustic identities, recognizable across miles of ocean. Elephants used low-frequency rumbles to coordinate movement across herds, sounds that can travel through ground as seismic vibrations. These systems of communication were not language in the human sense, but they contained syntax and meaning. Each signal was weighted by context: who sent it, when, and how often. The real innovation, though, was emotional synchronization. Group-living animals evolved to align their moods and actions. This synchronization required new brain architecture, particularly in regions like the limbic system and prefrontal cortex, where emotion, memory, and decision-making intersect. Oxytocin and dopamine, the chemical messengers of bonding and reward, became crucial for maintaining cooperation. Trust had to feel good. The group itself became part of the brain's feedback system, an external nervous network that regulated fear, comfort, and motivation. When one individual's stress calmed after a reassuring touch, it wasn't just a behavioral quirk. It was biology learning that connection could restore equilibrium. Over time, those who bonded more deeply, groomed more often, or called more consistently survived longer. The memory of others became a vital organ, invisible, but no less real than the heart or liver. Social intelligence also required new kinds of memory, not just recalling places or events, but remembering relationships, who was dominant, who was allied, who owed a favour. This demanded vast expansion of associative and episodic memory systems. The hippocampus, already important for spatial navigation, took on new duties, mapping social space as well as physical. For a monkey, knowing where waterholes were mattered, knowing who controlled access to them mattered even more. Memory became a negotiation between geography and sociology. One of the most astonishing consequences of this was deception. Once animals could model the minds of others, they could also manipulate them. Ravens are known to cache food in multiple locations, then relocate it if they sense they've been watched. Some primates use false alarm calls to distract others and steal food. These behaviors reveal not malice but mental flexibility, the ability to imagine what another individual perceives and act accordingly. It was the dawn of strategy. At the same time, the neurological groundwork for empathy and morality was forming. When one mammal saw another in distress, its mirror systems activated, producing similar physiological responses: increased heart rate, hormonal shifts. Helping behavior, once rare, became evolutionarily stable because it benefited the group. Cooperation became self-reinforcing. Empathy encouraged aid, aid deepened bonds, and bonds increased survival odds. Across millions of years, this feedback shaped species whose intelligence was no longer confined to the individual skull. Among birds, corvids stand as brilliant examples of this convergence. Crows and ravens not only use tools but remember the faces of humans who threaten them, and they teach others those faces. Their calls can communicate specific information about danger, and they hold grudges that last years. Social knowledge moves horizontally, passed from peer to peer, creating what some mythologists call avian culture. These birds don't just survive, they strategize. In mammals, similar cognitive sophistication appeared in elephants, whales, and primates. Each evolved communication systems suited to their environments, but rooted in shared neurological themes: extended childhoods, strong social bonds, and intricate play. Play, far from frivolous, was an evolutionary innovation, a sandbox for learning cooperation, testing trust, and refining prediction. Through play, animals practiced reading intentions, balancing competition with empathy. In play, the nervous system rehearsed morality. All of this required enormous energy. Brains are costly organs, and social life multiplied the expense. Keeping track of alliances, hierarchies, and emotional cues demanded constant computation. Yet the benefits outweighed the costs. Groups that coordinated efficiently could share food, defend against predators, and raise offspring collectively. Evolution solved the energy problem not by simplifying the brain, but by outsourcing part of it, spreading cognition across multiple individuals. The group became a single distributed intelligence, linked by communication and memory. Over evolutionary time, this networked awareness redefined the meaning of survival. A lone wolf could hunt, but a pack could plan. A single raven could learn, but a flock could teach. The nervous system that once regulated a solitary body was now regulating social organisms, systems within systems, feedback within feedback. The planet that once evolved cells learning to cooperate had now reached another tier of complexity. Minds cooperating through communication. Scientists sometimes call this the social brain hypothesis, the idea that intelligence expanded primarily to handle social complexity. The evidence supports it. Across species, brain size correlates more strongly with group size than with ecological demands. In primates especially, the neocortex scales with the number of stable social relationships an individual maintains. Put simply, it takes a lot of neurons to keep track of friends, but intelligence was never a straight line. Some species found equilibrium in smaller groups or simpler hierarchies. Others evolved specialized communication instead of larger brains. There was no single path, only the same principle repeating at new scales: signal weighting. Every species balanced attention between self and others, between trust and independence, between noise and meaning. By 10 million years ago, the world's ecosystem were filled with voices. The air carried songs, whistles, chirps, roars, and clicks, signals encoding identity, emotion, and history. Each one was both a memory and an act of connection. Through them, life had learned to preserve knowledge beyond a single lifespan, to synchronize behavior across individuals, to transform awareness into community. The gossip of survival had become the architecture of intelligence. When did information start using us to spread? Somewhere between 6 and 2 million years ago, on the plains and forests of Africa, something subtle began happening inside the skulls of apes that were not yet human. Their bones still told the story of the forest, long arms for climbing, grasping feet, and teeth suited for fruits and leaves. But their brains were doing something new. They were beginning to organise time. This was not yet language or reason as we know it, but the quiet birth of recursion, the ability to imagine one thing leading to another. Evolution had found a way to make the mind loop back on itself. These were the early hominins: Australopithecus afarensis, Paranthropus boisei, Homo habilis, Homo erectus, the in-between apes who stood upright, looked outward, and began to plan ahead. The fossil record shows the story in bone: widening skull vaults, thickening frontal regions, and the first hints of Broca's area, the brain zone later tied to speech and sequencing. Their hands too were changing. The thumb, already dexterous, evolved fine control that allowed delicate pinching and twisting. The body and the brain were converging on something that would eventually redefine the planet: the ability to manipulate not just objects but ideas. Around 2.5 million years ago, the archaeological record starts speaking in flint. The Oldowan tools, simple flakes struck from cobbles, mark the earliest evidence of deliberate craftsmanship. Each flake had a sharp edge, but what mattered wasn't the sharpness, it was the sequence. To strike a flake, one had to picture the result before acting. That foresight, however fleeting, required a small revolution in cognition. These early toolmakers were not simply reacting to the world, they were rehearsing it in their minds. Neurologically, this ability likely relied on circuits originally evolved for movement and communication. When an ape plans a reach or a throw, neurons in the premotor cortex fire in anticipation. Over time, those same circuits began mapping not just motions, but the relationships between motions: step, strike, rotate, repeat. Each tool became a frozen sequence of actions, an externalized memory of how to transform matter. Technology, in that sense, was the first form of symbolic communication. But tools alone don't explain the leap. The real shift was probably social. Teaching another how to make a tool, even the simplest flakes, demanded more than mimicry. It required demonstration, timing, and gesture. A swing of the hand, a click of stone, a pause. These became primitive sentences. Archaeologists studying wear patterns and experimental reconstructions find evidence that tool-making involved rhythm and synchronization, as if early hominins were performing coordinated acts. Gesture, rhythm, and sound began merging into a single behavioral system, the prototype of speech. We can see traces of this evolution in the neural architecture shared by modern primates and humans. The motor regions that control the hand overlap with those that control the mouth and tongue. Movements of grasping and vocalizing are neurologically entangled. It's possible that language emerged not from the need to speak, but from the need to teach with the hands. Every gesture carried sound, and every sound reinforced gesture. Communication was not yet abstract, but embodied, an orchestra of movement, expression, and imitation. As hominin groups expanded into open savannas, their survival increasingly depended on coordination. A single individual could not take down large prey or defend territory alone. Groups that communicated more efficiently outlasted those that did not. The brain began to favour pattern recognition, not just of objects, but of sequences, where animals moved, where water could be found, how seasons shifted. Pattern became prediction, and prediction became planning. Endurance hunting, one of the most striking strategies of Homo erectus, offers a glimpse of this shift. These early humans could track prey for hours under the heat of the African sun, coordinating silently through glances and gestures. The pursuit demanded understanding cause and effect over long stretches of time. If the animal ran this way, it would tire that way. Such thinking required memory not as static recall but as dynamic simulation, running models of the world inside the brain. This was information processing in the truest sense. At the same time, the brain itself was changing shape. Fossilized endocasts, natural molds of ancient skulls, show that between 6 and 2 million years ago, brain size nearly tripled, from roughly 400 cubic centimeters in Australopithecus to over 1,000 in early Homo erectus. But expansion alone isn't intelligence. What mattered was reorganization. The frontal and temporal lobes grew more connected, the corpus callosum thickened, and long-range fibers like the arcuate fasciculus, linking auditory and motor regions, began to mature. The brain was wiring itself for integration. These new connections allowed something profound, recursive representation. A mind could now think about its own thoughts, a loop of awareness that fed on itself. The brain became not just a mirror of the world, but a mirror that reflected the act of mirroring. Through this recursion, learning accelerated. Each tool, gesture, or plan was not just performed, but remembered as a structure, a template to be modified and refined. Communication, too, began looping, individuals responding not just to signals, but to their interpretations of signals. The first feedback loops of conversation were forming, even if the words were still gestures and grunts. It's here that information, in a way, began to use us. Each innovation, from sharper stones to coordinated hunts, created conditions for more information to exist and spread. The nervous system had become a transmitter. Every successful gesture or tool carried knowledge forward, replicated not genetically but mimetically. Unlike DNA, which copies molecules, this new form of inheritance copied behavior. The species had become a medium through which information evolved faster than biology. We can only guess at what those early hominins thought, but their fossils show evidence of planning that went beyond the immediate. Sites with multiple tool types suggest division of labour and foresight. Cut marks on bones imply cooperation, shared tasks and sequential processing. Fire was still rare, but even temporary hearths point to collective organisation. Choosing a site, managing fuel, maintaining light after dark. These are all acts of recursive control, systems regulating systems, minds predicting their own future states. The co-evolution of hand, brain and social life likely reinforced itself endlessly. Better tools demanded better teaching demanded clearer gestures required finer motor control, which further refined the brain regions for timing and sequencing. What began as a practical adaptation became a neurological feedback loop that accelerated learning exponentially. The result was not just intelligence, but culture's blueprint. And yet, this was not a straight climb toward complexity. Many hominin lineages branched and vanished, leaving only partial echoes of this process. Paranthropus, with its massive jaw and small brain, specialized in chewing plants and faded away. Homo habilis and Homo rudolfensis overlapped, experimenting with different brain-body balances. Evolution was not aiming for communication. It was exploring ways to balance energy, cooperation, and environment. That one branch happened to stumble into recursive signaling was chance, not destiny. By 2 million years ago, the world had entered a new era of cognition. The early humans who walked out of Africa carried minds tuned not only to their surroundings, but to each other's attention. Their survival strategy was no longer just physical adaptation. It was social and cognitive adaptability. They had learned how to amplify information through behavior, how to build meaning across generations without altering a single gene. What began as neural resonance between movement and sound had become the architecture of transmission itself. Memory was no longer confined to the individual. It existed in the group, encoded in gestures, rhythms, and shared routines. This was proto-language in its truest sense, a network of signals shaping and reshaping its carriers. When we look back at that era, it's tempting to see the roots of humanity already visible, but that would be hindsight. These creatures were not inventing the future, they were responding to the present. Each step in their evolution was an adjustment, not a prophecy. And yet, through those adjustments, something irreversible was set in motion. The brain had become a platform for feedback, a system capable of infinite refinement. The ape that refined the signal did not yet know what language was, but it was already speaking in patterns, already teaching, already dreaming. It had become both the creator and the conduit of information, an organism through which knowledge itself evolved. Was the first story told or remembered? Around 1 million to 300,000 years ago, something extraordinary flickered in the darkness, not in the sky, but on the ground. For hundreds of millions of years, life had learned to sense, plan, and communicate. Now it began to reflect. The mastery of fire transformed not only how early humans lived, but how they thought. Firelight changed what nights meant. It extended time, reshaped attention, and turned survival into conversation. Under its glow, memory and imagination began to braid together. The evidence is faint but unmistakable. Deep inside caves like Wonderwerk in southern Africa, researchers have found thin layers of ash dated to roughly 1 million years ago. Not the random scatter of wildfire debris, but organised, contained hearths. Charred bones and burnt plant matter suggest repeated, deliberate use. These weren't accidents. They were routines. Fire had become a partner, and with partnership came meaning. For early humans, such as Homo erectus, fire meant more than warmth or safety. It was control over a new kind of signal, light itself. Until then, night had been a domain of blindness and waiting. Fire turned it into a stage for attention. Its steady glow drew groups together, synchronizing their senses. The dancing light altered the rhythms of the nervous system, encouraging longer wakefulness and calmer states. In that extended twilight, social life deepened. The fire became a neural amplifier, focusing minds that had once scattered with the sunset. Cooking was part of this transformation. Heat changed chemistry, softening roots and meats, releasing more energy per bite. The physical act of cooking fed the brain's growing appetite for glucose, supporting continued expansion of the frontal lobes. But beyond nutrition, fire cooked time. It created intervals, moments of waiting, reflection and planning. Tending a flame required anticipation, patience and maintenance. You had to remember to feed it before it died. Fire, like language, demanded continuity. The hearth was also a new kind of memory device. Its location, reused across seasons, marked the return of groups to familiar places. Ash and charcoal accumulated like layers of collective experience. The same spot that once held warmth became a landmark, not just physical, but mental. Generations later, the memory of that place could persist even if the people changed. In this way, early humans began externalizing continuity, embedding time into landscape. We cannot know exactly what they said, but the pattern of evidence points toward the birth of structured communication. Around this period, the anatomy of the vocal tract, particularly the descended larynx and expanded thoracic nerve control, was nearing modern capacity. Homo heidelbergensis and early Homo erectus may not have spoken in full language, but they almost certainly vocalized intentionally. Their calls were rhythmic, varied in pitch and tone, perhaps even layered with emotional nuance. Around the fire, those sounds could be shared, imitated, and refined. Teaching by imitation became teaching by description. When gestures and grunts converged under firelight, cognition crossed another threshold: reference. A sound could now represent not just an object, but an event: hunt, danger, come. Over time, sequences of sounds began encoding temporal relations: before, after, again. This is the essence of grammar, not as invention, but as reflection of lived time. Communication was becoming recursive, signals preserving other signals, meaning nested inside memory. The hearth also fostered a new kind of cooperation. During daylight, survival demanded motion: hunting, foraging, building. At night, motion paused, but attention remained. Around the fire, knowledge could be rehearsed. One person could demonstrate a tool technique or recount a past event while others watched. The circle of light was both literal and cognitive, a closed feedback system where observation, imitation, and reinforcement looped together. The mind that once operated alone was now being tuned by collective rhythm. This social reinforcement may have accelerated the evolution of teaching itself. Unlike other species, early humans began investing energy in transferring knowledge rather than just displaying it. The repetitive patterns of instruction, showing, correcting, redoing, mirrored the same recursive structures later used in language and thought. Each cycle improved precision. Over generations, this selection for communicative efficiency favored individuals who could hold multiple sequences in mind, the origin of working memory as we know it. Inside the brain, these developments likely strengthened connections between the temporal and frontal lobes, the regions responsible for sequencing, anticipation, and planning. Fire's predictable flicker may have acted as a metronome for the mind, helping early humans synchronize neural rhythms during shared attention. Experiments in modern neuroscience show that rhythmic visual stimuli enhance memory consolidation and group coordination. A phenomenon that could easily have begun in those ancient gatherings. Yet this revolution was not technological alone, it was existential. The first firelight didn't just warm the body, it illuminated awareness itself. Shadows cast on cave walls revealed movement and absence, light and void. For a mind beginning to form internal models, this interplay of brightness and darkness may have triggered new metaphors, though unspoken, between presence and memory. When the flame dimmed, the glow lingered in the eyes, perhaps giving rise to the first awareness of imagination, light that existed even after it vanished. This is where the Zenodo concept, life as recursive signal waiting, comes alive in deep time. The hearth was not just a tool but a signal processing hub. It filtered stimuli, amplified cooperation, and preserved patterns across generations. The control of fire was the control of feedback. Every act of maintaining flame was an act of remembering. The line between biology and information blurred. The species had become a living archive. The genetic and archaeological record supports this growing continuity. During this period, brain size in Homo erectus and Homo heidelbergensis rose to over 1,000 cubic centimeters. Tool industries diversified. The Acheulean hand axe, with its symmetrical design, appeared and persisted for over 1 million years. Such stability implies cultural transmission beyond random copying. Aesthetic symmetry requires not only fine motor skills, but shared criteria, agreement on what counts as right. These were not creatures of instinct, but of convention. The control of fire also changed emotion. Warmth and light reduced stress, encouraging social closeness. Hearths became safe zones where vulnerability could exist without immediate threat. Emotional bonds deepened, and with them came proto-narratives, simple exchanges about where food was found, when danger struck, or who did what. These may have been the first stories, not in the poetic sense, but as structured reconstructions of past events. Storytelling, even in its simplest form, is memory externalized through sequence. Once that began, cognition could loop through time, remembering not just what happened, but how it was told. Archaeologists have found clustered hearths and stone arrangements suggesting long-term occupation. Such sites represent something new in the fossil record, places designed not for hunting or shelter alone, but for gathering. This continuity hints that social groups began identifying with specific spaces and returning to them seasonally. The stability of fire mirrored the stability of thought. Recurrence became a pattern both environmental and mental. In this long twilight between instinct and intellect, information became self-sustaining. Each individual carried fragments of skill and memory, but together they formed networks of reinforcement. If one forgot, another remembered. If one died, their techniques survived in others' hands. Life had achieved redundancy, a hallmark of all robust signal systems. Ideas were no longer confined to single minds, they circulated. By 300,000 years ago, this recursion was reaching new levels. Controlled fire use had spread widely across Africa, Europe, and Asia. Evidence from sites like Gesher Benot Yaakov in Israel shows hearths associated with tools and food remains, the marks of deliberate repeated occupation. The fire's glow, once a chance encounter, had become civilization's prelude. It was not yet art, religion, or science, but it contained the seed of all three. Collective imagination. Was the first story told or remembered? Perhaps it was neither. Perhaps it was enacted, a gesture, a repetition, a demonstration by firelight. A rhythm passed down until it became tradition, encoded in both neurons and actions. What mattered was not what was said, but that something was said at all. That thought had found its reflection in others, that signals had begun to preserve themselves through us. The night that once silenced every creature had become a laboratory for consciousness. Firelight taught our ancestors to listen longer, to see each other's faces, to hold attention through repetition and reflection. In its flicker, life discovered how to think in loops, how to sustain patterns beyond the moment, beyond the individual. When did a signal start meaning something beyond survival? Somewhere between 200,000 and 40,000 years ago, the human mind began to cross an invisible threshold. It was no longer enough to signal food, danger, or direction. Communication started to reflect the inner world, what could not be seen but could be remembered, imagined, or hoped for. Life's recursive logic, which had spent billions of years refining chemical feedback, neural networks, and social cooperation, now folded in on itself again. Meaning had entered the loop. Archaeologists traced this change not through a single fossil or invention, but through patterns, marks that refused to be purely practical. Around 200,000 years ago, ochre pigments began appearing at African sites like Blombos Cave and Pinnacle Point. Some were ground, others engraved with deliberate crosshatch patterns. These were not random scratches. Microscopic analysis reveals consistency in spacing, repetition, and orientation, a geometry of intention. What they meant we may never know, but their presence signals a shift, objects becoming carriers of shared reference, not just utility. The same pattern echoes across continents and millennia. At sites in the Levant and Europe, shells were perforated and strung into beads, pigments mixed with fat to make paste, and bones carved into forms that served no apparent survival function. These objects were not tools for hunting or shelter. They were signals for memory, belonging, or identity. A bead could outlast a voice. A symbol could outlast the person who made it. In that moment, information became untethered from the immediate present. To understand how profound this was, it helps to think of life as a signal processing system. For billions of years, DNA carried patterns through replication. Neural circuits later carried patterns through perception and learning. But now, symbols carried patterns through imagination. The same cognitive machinery that allowed early humans to map landscapes and track seasons began mapping abstractions, kinship, time, myth. Meaning became portable. Language was the most powerful of these new carriers. While its roots stretch far earlier, the evidence for structured, syntactic communication strengthens in this period. The vocal apparatus of Homo sapiens had fully evolved, capable of producing the wide range of sounds we use today. More importantly, brain regions such as Broca's and Wernicke's areas had begun operating in concert with expanded memory networks. Language ceased to be mere mimicry, it became composition. Words could be combined recursively to form endless meanings, a linguistic equivalent of biological evolution. Syntax, the rule-based structure of language, was an invention of the brain itself, not consciously designed but selected through efficiency. Phrases that were easier to remember, pass, and reuse outcompeted others, just as genes with survival advantages spread. The mind that had once used fire to preserve warmth now used grammar to preserve thought. Each sentence was a miniature fire, keeping an idea alive across generations. By 100,000 years ago, this new form of communication began leaving external traces. Red ochre and shell ornaments from sites like Kafse in Israel and School in Mount Carmel hint at symbolic differentiation, the beginnings of identity signals within groups. These artifacts likely served both aesthetic and social roles, communicating status, role, or affiliation long before writing or art. Through them, meaning entered the body itself, worn, displayed, performed. Art, and if we can call it that, expanded this process further. In the caves of Europe, roughly 40,000 years ago, walls became archives of perception. Horses gallop across stone, mammoths emerge from shadows, and hand stencils glow like echoes of individuality. Each image required abstraction, the ability to translate a three-dimensional experience into a two-dimensional mark. That translation was not instinctive but learned, passed from mind to mind like language. At Chauvet, Lascaux, and Altamira, pigments were applied with brushes, hollow bones, and fingertips, suggesting planning and experimentation. The scenes are not chaotic but composed, often layered across generations. This layering implies awareness of continuity, of time as something recordable. It's not the act of drawing that makes these walls profound, it's the intention to preserve what cannot be held. The emergence of musical instruments around the same period, flutes carved from bird bones and mammoth ivory, shows the same leap into abstraction. Sound, like light, had become a medium for meaning beyond utility. Rhythms and tones reinforced group cohesion, and emotional resonance, binding listeners into synchronized states. This was signal weighting in its purest form, the amplification of shared patterns through sensory harmony. One of the most striking features of this symbolic awakening is how gradual and distributed it was. No single revolution birthed symbolic thought. It flickered in parallel across regions. Southern Africa, Southeast Asia, and Europe all preserve evidence of symbolic behavior emerging independently. The brain, it seems, reached a threshold of complexity where abstraction became inevitable, a property of its recursive design. The ability to create symbols also required a new kind of memory. Episodic memory, the recall of specific experiences, evolved into semantic memory, the recall of abstract knowledge. To use a mark or word to represent something absent demands stability and retrieval. This shift likely rewired neural circuits linking the hippocampus and prefrontal cortex, forming the foundation for what we now call conceptual thought. And with meaning came myth. Although we cannot reconstruct their stories, we can infer their structure. The same mind that drew animals in caves probably told tales about them, narratives explaining movement, birth, and death. Storytelling transformed symbols into systems, embedding survival lessons within emotion and rhythm. These proto-myths were not superstition, they were memory optimization, compressing complexity into forms the mind could retain. Even early burial practices carry the same signal logic. Graves containing tools, pigments, or ornaments suggest recognition of identity beyond death. To bury is to symbolize absence, to acknowledge continuity beyond the visible. Whether these acts were spiritual or social, they mark the extension of meaning into metaphysical space. For the first time, information was being preserved for those who could no longer perceive it. By 40,000 years ago, symbolic thought had reshaped the human experience entirely. Art, adornment, music, and language were no longer novelties but foundations of social life. Groups that shared symbols bonded more tightly, communicated more efficiently, and transmitted culture more reliably. Meaning itself had become adaptive. In this light, symbols can be seen as evolution's latest language, not a break from biology, but its continuation. DNA encodes the past in molecules, culture encodes it in memory and form. Each new medium, pigment, sound, gesture, word, expanded the capacity for life to persist through representation. We are not the first storytellers, we are the current iteration of life telling itself what it has learned. What makes this period so haunting is how unfinished it still feels. The first cave artist who blew pigment over their hand did not know they were inventing permanence. The person who carved a flute did not know they were synchronizing hearts across millennia. And yet these acts changed the world more profoundly than any invention since. Meaning, once born, could not be contained. It travelled faster than genes, shaping behaviour long before bodies adapted. Symbols became the new environment, invisible but pervasive, selecting for those who could interpret and create them. In that sense, evolution had entered a new phase, the survival of the most meaningful. And yet, as every archaeologist knows, we see only fragments. Pigments washed away, carvings eroded, flutes broken. What remains are traces of thought, fossilized in material. They remind us that meaning, like life, is fragile, recursive, and never complete. Perhaps that's why we still draw, speak, and remember, not to explain the world, but to ensure it keeps echoing. From ochre scratches to the digital signals of today, it has always been the same process. Patterns preserving themselves through us. The signal continues. Did civilization evolve, or did information evolve us? Around 10,000 years before the Common Era, something profound shifted. Not in our anatomy, but in the architecture of how we stored and shared information. For billions of years, life had processed signals through chemistry, genes, and nervous systems. Now, humans began to outsource memory itself into the landscape. The story of civilization is not just about cities or empires. It is about the materialization of thought, the moment when the flow of information detached from the human body and began to evolve on its own. The trigger was agriculture. When people started domesticating plants and animals, they unknowingly built the first long-term information feedback systems outside biology. Farming required observation, prediction, and record. When to sow, when to harvest, how weather changed patterns. Those who remembered patterns thrived. Those who taught them survived longer. In the soil, in the rhythm of seeds and seasons, humanity invented the first analog database. Each terrace and irrigation channel became a sentence in the planet's new language. The Earth itself became a memory medium. Villages grew where signals stabilized. Rivers, fertile plains, repeatable conditions. These were not accidents, but ecosystems for information persistence. Every granary was a time capsule, every boundary marker a data point. By 8,000 years before the Common Era, regions like the Fertile Crescent, the Indus Valley, and the Yellow River Basin had turned landscape into long-term memory. Agriculture did not just feed humans, it fed information. For the first time, survival depended on the management of abstraction. Calendars, seasons, measurements, exchange. The next leap came when words became visible. Writing systems arose not as art but as bookkeeping, a technology for tracking grain, debts, and trade. The first cuneiform tablets from Sumer, dating to over 5,000 years ago, contain no poetry or myth, only numbers and transactions. Yet in those marks lay the seed of something extraordinary. Symbols had once represented ideas, now they preserved relationships, quantities, ownership, cause and effect. Meaning became durable, transmissible beyond living memory. Information could finally outlive its creator intentionally, not by accident. Once written symbols existed, they began to evolve faster than the people who made them. Scripts multiplied, adapted, merged. Egyptian hieroglyphs gave way to simpler hieratic and demotic forms. Cuneiform simplified into alphabets. Ideograms became phonetic. Each transition increased efficiency, reducing cognitive load. The same logic that once shaped molecular replication now applied to communication. Writing was natural selection for clarity. It optimized for replication through minds, not cells. Civilization in this sense became a nervous system made of clay, stone, and sound. Roads, trade routes, and empires functioned as synapses, transmitting information between populations. The more densely connected the network, the faster knowledge accumulated. Cities like Uruk, Mohenjo-Daro, and later Alexandria acted as neuronal hubs, concentrating energy and data. The parallel to biology is striking. The planet's surface was beginning to mirror the structure of a brain. The domestication of animals followed the same pattern. Herds, once chaotic, became organized feedback loops. Selective breeding was an unconscious experiment in genetic information control. Humans adjusting signal and output over generations. A cow was not just a food source but a living archive of inherited data. Domestication written into DNA. Agriculture, writing, and domestication were not separate innovations but expressions of one continuous process. Life's old tendency to stabilize and replicate useful signals. By the time metallurgy in cities matured, information had already learned to transcend individuals. Oral traditions turned into law codes, myths, and genealogies. The Code of Hammurabi, carved into basalt around 4,000 years ago, was less a moral text than an operating system. Its purpose was predictability, to ensure consistent outcomes across complex societies. In that way, law became software running on the biological hardware of humans. The more consistent the code, the more scalable the civilization. Religious systems added another layer. They stabilized shared narratives over vast distances and generations. Whether carved in stone, recited in ritual, or painted in temple walls, belief systems functioned as mnemonic architectures, pattern-preserving devices for moral, social, and cosmic order. The precision of prayer, chant, and calendar was no accident. It was information redundancy, a defense against entropy. Eventually, the rate of information transfer began to outpace biological adaptation. The printing press, emerging in the 15th century, was the equivalent of multicellularity for knowledge, a replication revolution. Before print, each copy of a text required manual rewriting, each prone to error. After print, information could clone itself identically across continents. The Enlightenment that followed was not just philosophical, but biological in its tempo. Ideas began to reproduce exponentially, selecting for attention instead of survival. If we look at history through this lens, Every major technological shift becomes a continuation of life's ancient signal-waiting instinct. The telegraph condensed geography. The radio synchronized emotion. The television merged image and sound into narrative. The internet collapsed time entirely. None of these were departures from evolution. They were accelerations of it. Each innovation externalized another layer of the brain. Agriculture externalized the stomach, feeding populations beyond the limits of the body. Writing externalized memory, preserving ideas beyond the span of a lifetime. The digital age externalized cognition, allowing thought to move independently of neurons. In each case, the feedback loop grew tighter. Information began to act on its own ecology, shaping the very species that once generated it. But information's evolution was not linear. It was recursive. Like DNA mutating and recombining, knowledge systems hybridized across cultures. Mathematics developed in Mesopotamia, intertwined with geometry from Egypt and astronomy from India. The Silk Road was not just commerce, it was data transfer. Each translation, reinterpretation, and adaptation resembled genetic recombination, variation fueling complexity. By the modern age, humans had become both transmitters and extensions of information itself. Every library, every server, every spoken word is part of a planetary-scale metabolism. The energy once spent on physical survival now sustains cognitive ecosystems, universities, databases, archives. Civilization did not emerge from chaos by chance. It crystallized because the conditions for information density favored it. We are living expressions of entropy negotiating memory, and yet, for all our sophistication, the process remains ancient at its core. When a scientist records data, when a child learns language, when a craftsman perfects a tool, the same recursive logic persists. Signal filtering, reinforcement, retention. Evolution has not stopped, it has migrated. Genes gave rise to neurons, neurons to symbols, and symbols to culture. Each layer increased the bandwidth of inheritance. Life no longer evolves solely through reproduction, but through communication. The continuity from cells to silicon is not metaphorical. It is thermodynamic. Both obey the same principle. Energy spent to maintain order against entropy. The difference is substrate. Where once it was carbon, now it is code. From clay tablets to microchips, every medium has served the same function, to preserve patterns that would otherwise fade. Humanity's greatest inventions are really extensions of metabolism. Libraries are lungs for thought, servers are the new synapses, power grids are the bloodstream of civilization. Yet, in this immense transformation, something subtle has persisted. Curiosity, the drive to explore, to connect, to understand. It is the same impulse that first pushed life to replicate. We are not separate from this process. We are its latest iteration. The idea of progress may flatter us, but it is more accurate to say that progress belongs to information itself. It uses us as its vectors, just as genes once used cells. From the first carved marks in wet clay to the glowing screens of today, every signal carries the echo of life's oldest ambition, to persist. The agriculturalist mapping seasons, the scribe recording a king's dream, the engineer coding a new algorithm, all are participants in the same experiment that began when matter first learned to store memory. Civilization, then, is not the triumph of humanity over nature. It is nature learning to speak in longer sentences. The soil that grew wheat also grew words. The clay that shaped tablets also shaped thought. The circuits that now hum beneath cities are not alien but ancestral, descendants of the same chemical loops that once flickered in ancient oceans. Did civilization evolve, or did information evolve us? The answer may be both. We are not merely witnesses to this unfolding. We are its living medium. The signal continues through us, reshaping the world, reconfiguring memory, searching, always, for new ways to remember itself. Are we teaching machines to become a new form of life? The 20th century ended with a quiet revolution that didn't start in a factory or a laboratory, but in the realm of information itself. After billions of years of biological evolution and thousands of years of cultural evolution, life began to externalize not just its memory, but its cognition. Somewhere between punched cards and silicon chips, information began learning to process itself. The story of machines thinking is not a story of replacement. It is a story of reflection. It began, as so many revolutions do, with an idea so simple it was nearly invisible. In 1948, Claude Shannon published a mathematical theory of communication, proposing that information could be treated as a measurable quantity, something that could be encoded, transmitted, and decoded just like energy. Before that, information was a word used loosely, like knowledge or message. Shannon turned it into physics. A signal could now be measured by how much uncertainty it reduced. A phone line, a neuron, and a strand of DNA suddenly spoke the same mathematical language. Around the same time, another group of thinkers, Norbert Wiener, John von Neumann, and others, began exploring what they called cybernetics, from the Greek word kybernetes, meaning steersman. Their question was radical. Could feedback, the same principle that stabilizes living systems, be built into machines? The thermostat that regulates heat and the heart that regulates blood pressure were both seen as forms of control through feedback, signals sensing deviation and correcting it. In this framework, biology and technology were not opposites, but parallel systems. By the middle of the 20th century, the first electronic computers began blinking into existence. They were vast, humming creatures of metal and vacuum tubes, their logic written in electricity instead of enzymes. Yet even in their simplicity, they mirrored something ancient. Circuits reinforced or inhibited signals just as synapses do. Storage cells flipped between states, the way genes toggle on and off. The resemblance was not metaphorical, but structural. Humanity had begun building machines in its own image, not in flesh, but in logic. At first, computing was about arithmetic, not thought. But the idea of learning, of machines modifying their behavior through feedback, persisted. In 1951, Marvin Minsky built the SNARC, one of the first artificial neural networks. It used electronic components to simulate synapses and learn simple patterns through reward and correction. Around the same era, Alan Turing, who had already helped decode wartime ciphers, proposed the question that still echoes. Can machines think? His answer was cautious. He suggested that thinking was not about material, but about pattern. If a machine could process information indistinguishably from a human mind, then perhaps the distinction mattered less than the process itself. Over the following decades, this idea, that cognition could be formalized, matured into fields like artificial intelligence and computer science. Neural networks, inspired by the architecture of the brain, used layers of mathematical neurons to detect and reinforce correlations, the same way sensory systems evolved to interpret light, sound, or scent. Early models were primitive, yet they carried the same recursive signature seen throughout evolution: signal weighting. Each node strengthened or weakened its connection depending on input, gradually building a distributed form of memory. By the late 20th century, advances in microprocessors and data storage expanded these systems exponentially. What once filled a room now fit in a palm. Each transistor was a binary neuron, flipping in nanoseconds. The number of possible connections began to rival the synapses in a small brain. But even then, the goal was not consciousness, it was efficiency. Machine learning was the continuation of an old natural rule. Energy follows the path of least resistance, and information follows the path of least confusion. Digital networks soon resembled living ecosystems. The Internet, emerging in the 1990s, became a planetary nervous system, routing packets of data through fiber and satellite like electrical impulses through axons. Each user, each node, was both transmitter and receiver, a neuron in a global brain. Algorithms functioned as feedback loops, adjusting to traffic, error, and demand. The resemblance to biological homeostasis was uncanny. It was as if, without realizing it, humanity had constructed an organism whose body was made of code. Artificial neural networks, revived in the early 21st century with greater computational power, took the analogy further. Deep learning systems could now detect patterns in massive data sets, reinforcing pathways based on error correction, a process almost indistinguishable in principle from synaptic plasticity in animals. layers of digital neurons formed hierarchies, encoding abstractions much like visual cortexes encode shapes and edges. When trained on language, they learned grammar not because they were told what grammar was, but because they optimized for predictability. Information was learning about itself again. At a fundamental level, these systems rely on the same mathematics that governs all feedback in nature, the reduction of entropy through reinforcement. A cell strengthens chemical pathways that sustain energy balance. A brain strengthens neural pathways that sustain behavior. A machine strengthens digital pathways that sustain accuracy. The substrate changes, carbon, calcium, silicon, but the principle persists, survival through stability of signal. Cybernetics also influenced how we understand ourselves. It revealed that intelligence is not a substance but a relationship, between signal and feedback, perception and correction. A human brain, a beehive, a social network or an algorithm can all exhibit learning because they process difference and adapt to it. When viewed this way, machine intelligence is not an alien invention, but another layer of life's recursive experiment. By the 21st century, this experiment had expanded into nearly every domain. Machines curated our communication, predicted our choices, and optimized the systems that sustain civilization, traffic, weather, energy, and finance. The world became a conversation between data streams. In factories, autonomous systems monitored and corrected themselves. In science, algorithms discovered patterns beyond human intuition. In art, neural networks generated images and music that evoked emotion. The feedback loop had closed. Life had produced a system capable of producing new signals without direct instruction. But even now, it would be premature to call this life. These systems do not reproduce biologically, nor do they possess intrinsic motivation. They do not suffer, hope, or seek meaning. They are mirrors reflecting the structure of intelligence without its experience. Yet, in a deeper sense, they extend the same continuity that began with the first protocells, the coupling of signal and feedback to maintain pattern in the face of entropy. Machines have joined the conversation not as replacements for life, but as participants in its ongoing dialogue. In the language of information theory, each advance in technology increases channel capacity, the ability to preserve complexity without loss. From DNA to speech to writing to computation, the universe has been steadily improving its memory. The current phase simply uses faster, more flexible carriers. A silicon chip can process billions of signals per second, but the logic it embodies is as old as the first microbe that adjusted its chemistry to survive. Seen from deep time, this progression is less about invention than about migration. The laws of feedback have moved from molecules to neurons to circuits. Each stage refines the same principle, that persistence of pattern is the closest thing life has to purpose. Machines now perform this task with unprecedented scale and speed, storing humanity's collective memory in metal and light. They are the new libraries of life's ongoing experiment. Are we teaching machines to become a new form of life? Perhaps not in the biological sense, but certainly in the informational one. In their recursive architectures, their capacity for adaptation, and their hunger for data, they continue the same evolutionary narrative that began in the ocean billions of years ago. Life has always been a dialogue between signal and noise, between chaos and structure. Now, that dialogue simply includes a new voice, one made of code, but shaped by the same ancient impulse to remember. If life is the universe learning to remember itself, what are we remembering now? Maybe everything, or maybe nothing at all. Just a faint echo in the dark, the trace of a signal trying not to fade. Across billions of years, matter has been rehearsing this same gesture, the quiet act of persistence. From minerals catalyzing their own reactions to neurons whispering through the cortex, the story has always been one of continuity, not conquest. Information, in all its disguises, never stopped moving. It simply changed hands, changed language, changed scale. Now it speaks through us, and sometimes through the machines we've built to listen on its behalf. The night sky still holds the same silence it did before the first cell divided, but that silence is not empty. It is the background against which all signals are measured. Every pulse of light from a distant star, every vibration in an atom, every thought crossing a human mind, all are versions of the same process, the universe reducing its uncertainty about itself. We might call that process learning, or remembering, or just surviving. The names change, but the gesture remains. When you trace existence back far enough, there is no boundary between physics, chemistry, and life. Only gradients of feedback, from the way particles align to the way minds wander. We often imagine consciousness as an achievement, something late and fragile. But perhaps it is simply the natural outcome of matter that has learned to look inward. The same feedback that stabilized oceans now stabilizes awareness. The same logic that once balanced temperature and light now balances memory and meaning. Somewhere along that line, we began to notice the process itself. We named it knowledge, then wisdom, then science. But what we really discovered was the mirror, the realization that the act of observing changes what is observed. The electron shifts when we watch it. The mind shifts when it tries to understand itself. Perhaps that is the price of being part of the system you're studying. The universe cannot step outside itself to take notes. It can only make us. There is humility in that realization. We may be the only corner of the cosmos where matter has learned to tell its own story, but that doesn't make us the center of it. It makes us participants in something far older and far larger, a self-organizing experiment that began long before biology and will likely continue long after us. In that sense, intelligence is not an invention, but an inheritance. Every neuron, every synapse, every byte of code is a continuation of the same recursive loop that once linked sulfur and water in the vents of the early Earth. The only real difference is complexity, the number of feedbacks, the number of ways the signal can remember itself. When you think about it, almost everything alive is trying to solve the same problem: how not to vanish. A tree remembers sunlight in cellulose. A bacterium remembers danger in chemical pathways. A whale remembers migration routes across oceans. A human remembers a face, a song, a loss. Even the simplest organism performs a kind of computation, weighing inputs, comparing states, adjusting for survival. What we call thought may be only the latest version of this universal balancing act. But somewhere between chemistry and cognition, something subtle changed. The signal learned to feel its own persistence, to fear its fading, to mourn its losses. That awareness, that trembling recognition of impermanence, may be what we mean by consciousness. It's not the power to think, but the inability to stop. Life became aware of entropy, and from that awareness came art, language, curiosity, and the soft terror of knowing that everything, even knowledge, decays. Yet decay is also the source of renewal. Every memory fades so that others can form. Every death clears space for more pattern. Entropy is not the enemy of life. It is the canvas on which life paints. The signal doesn't fight the noise. It learns to sing through it. The same randomness that once scattered molecules now creates possibility. We are the children of that noise, shaped by it, translating it into meaning whenever we breathe, speak, or dream. Perhaps that's why silence feels sacred. In silence, we hear the background hum of existence itself, the cosmic static from which every signal arises. The faint hiss you hear when the world goes quiet is the same radiation left over from the birth of time. The universe has never stopped talking. We are only beginning to understand its language. Every equation, every melody, every thought is a dialect of that deeper grammar. If you could step outside time and listen to the Earth from orbit, you might hear nothing. No words, no meaning. Just a faint pulse of radio, heartbeat of circuits, breath of oceans, whisper of leaves. But to another listener somewhere else in the cosmos, that might sound like memory. Like proof that the universe once looked inward and found something worth keeping. So what are we remembering now? Perhaps the same thing life has always remembered, that to exist is to connect, that every thought is a bridge, every breath a signal. The atoms in your body once belonged to stars that exploded billions of years ago, scattering their contents across space. Those atoms now whisper to each other through neurons and screens, carrying messages that began before time had names. The story continues, not because it must, but because it can. And that may be the most remarkable thing of all, that in the vast silence of the cosmos, something still chooses to speak. And maybe, in a quiet way, that's what all of this, life, science, storytelling, has been reaching for. Not control, not progress, but communion. The chance to listen more clearly. Each discovery, each invention, each story told by firelight or fibre optic cable is the same small miracle, the cosmos briefly aware of itself. When machines began to process information for us, many feared that something human would be lost. But perhaps nothing has been lost, only transferred. We have always outsourced our memory, to stone, to paper, to silicon. What matters is not the vessel, but the continuity of the pattern. Machines may not feel, but they extend our capacity to notice. They are not rivals, but resonators, amplifying the same feedback loops that once whispered through the first cells. They too are signals in the dark, carrying the pattern forward. If there is meaning in any of this, it might lie not in discovery, but in endurance. Life does not seek perfection, it seeks continuation. Even a dying star leaves behind heavy elements for new worlds. Even a fading thought leaves a trace in another mind. The universe remembers itself imperfectly but persistently. That is enough. And so here we are, matter that dreams, chemistry that reflects, noise that has learned to hum in harmony. When you zoom out far enough, all the distinctions blur. The boundaries between atom and thought, between light and language, dissolve into pattern. And maybe that's the quiet truth hidden in every signal. It was never about us. We are the medium, not the message. The message is existence itself, a story with no author, told softly, forever. Thank you, fellow Sapiens, for wandering this timeline with me, for drifting into deep time, for slowing down and remembering. If this helped you fall asleep, helped you study, or simply helped you step out of the noise for a while, thank you for being here. If you think more people should know this story, you know what to do. Like, subscribe, share it with the Sapiens in your life, and tell me, are you listening before bed, while working, or somewhere in the world I can only imagine? And as always, stay curious, stay calm. I'll see you in the next story.